Okay, good morning, Astronomy 1010, or rather Nina and Whitney and whoever the troll is in the background. That's only three of you, but I'm dedicated this week to doing the live experience to see how that goes. And, you know, if we can't get a few more fillies in the stable, we might farm this thing out to pre-recording, but today we'll do it right. This starts our first day of business where it's going to be a homework session, followed by a lecture, followed by a lab. So it's going to be a bit of a day. But then again, the alternative is worse, right? The alternative is we have to do all this stuff by ourselves. So what I was just saying to Nina and Whitney is over here in Blackboard, you have a little tab on the left called the homework tab. And in it, you can see homework number 1. I should probably activate homework number 2 as well, but oh, great. If you can right-click chapter2.pdf, you can see a scan from the book with some of the questions. I know some of you guys are still working on getting a book, and some of you might not even want to get a book. You might want to just try to, I don't know how else we say it, try to do the class raw without a book or a lab book, and that's okay. Do you guys have the calculators today? I guess that's the first thing. Yes. Whitney, don't let me down. Yes. Okay. All right. And you, who is that in the background there? That's Joey. Joey, you got that thing?
Yes, I do.
Yeah, I love it. Okay. And it's good to hear your voice as well. So let me hide the trolls here. Okay. What I'd like to do is I'm going to show you guys exactly how I want you to format this homework. And then I'll ask one of you to read the question. We'll talk about it. I realized when I woke up today, which was not that long ago, that this homework's going to suck a little bit because the first question we didn't quite cover, and the last 2 questions we didn't quite cover. And I started wondering, what the hell did I exactly do with you guys on Monday? I think I just took a little bit of too much time covering the stuff that I did cover. So that's okay. We can talk about it and learn about it as we go. It's not pretty, but it's doable. So here's what I'd like you to do. Let me check out the share screen here. And the 5 problems that were assigned is from chapter 2, 44, 48, 53, 57, 59. Remember those numbers for me, okay? Meanwhile, I'm going to show you guys how I'd like you to format this problem here. Where's the good marker? Okay. So at the top of the page, which you'll probably take a photo of and send to me after class or at the end of this session, let's put our name up there. That's important. Every time you write me an email or talk to me, I want you guys to remind me that you're in Astronomy 1010. If I have 28 times 2 students, that's almost 50 students, and it's just helpful to know which class you're in because I might get the names jumbled up with the classes there. And then this is homework number 1. It's always a very good idea to write that on the page so that you don't get confused when you're submitting assignments. Lots of people get confused when they're submitting assignments, and this can get messy as we go forward. And we're doing chapter 2, 44, 48. What were the other numbers, guys?
44, 48, 53, 57, and 59.
Okay, thank you. So I find it just helpful to put that stuff up at the top of the page. So when you quickly glance at this later, you'll remember what it was you were doing. Oh, that's the good black marker. I gotta segregate these markers. All right, so let's get right into it. Let's start with chapter 2, number 44. And what I'd like you to do, Whitney, since I just heard your lovely voice, could you read me the little title in italics and then just read me the question?
New planet. A planet is another solar system, has a circular orbit and an axis tilt of 35 degrees. Would you expect this planet to have seasons? If so, would you expect them to be more extreme than the seasons on Earth? If not, Why not?
Okay. Seasons, would they be more or less extreme, and why? I'm sorry, was the axis tilt 35 degrees?
Yes.
All right. This is a sort of essay problem or a little paragraph I call them word problems versus the math problems. But in any science problem that you have to solve, you can extract what we call the givens, just so you can organize the information. I like to do that. I find it's a classy thing. I want to remember we got a circular orbit. We got an axis tilt. That's one of the givens. And if you were paying close attention to the words, there's actually 3 sub-questions buried within the question. One is, does the planet have seasons? The second is, are those more or less extreme than Earth? And the third is why. Now, just to give you a heads up on how I grade these problems, I grade all of my problem sets out of 5 points. And I usually have in mind what I'm going to assign the points for, how well you addressed the little sub-questions within it. So this is your first question, and obviously it's not going to be an issue because you're going to do it with me and it's going to come out perfect, okay? But just to get you thinking about how to solve a problem like this, in my mind, I kind of pre-assigned, well, maybe I'll give them 2 points for addressing the season question correctly, maybe 2 points for answering whether or not it's extreme correctly, and then 1 point for why, which is actually the hardest part of this problem. But because it's hard, and it's your first problem, I'm only going to assign 1 point for that. But this just helps you understand where I'm coming from, Now, if you follow closely and write down everything I write down, then it's not going to be an issue. You're going to get 5 out of 5 points. But I wanted to start off by saying that so that you can understand that there is a system to how I grade these things, okay? Unfortunately, I didn't quite get to this subject in the lecture. I was teetering on the edge of it. For instance, you will remember that in our lecture, I did talk to you about Earth's axis tilt. Do we remember what Earth's axis tilt was? Before I show it to you?
No.
Damn, I thought that was like a thing. All right, well, look in your notes, Whitney. See if you can rustle it up. What's the axis tilt of Earth?
23.5.
Degrees, okay.
Oh, hold on.
Okay, was this the class where I kind of tricked someone about perihelion and aphelion? Was that you, Nina? Did I trick you, Nina?
Yes.
And I asked you to guess what month you thought perihelion might occur in, and you guessed something like July, right?
Yes.
All right, now that's where I should have segued into seasons, but there was another thing I wanted to do and I got distracted. So do you remember what I said about perihelion?
That in perihelion the sun is, or it's like January, and like
Yeah,
sun is closer, and then an aphelion is like August or July.
something like that. Yeah, I can't remember which one, unfortunately. So that tells you right away that it's not so much about the distance that causes seasons. And here's where I should have said a little more, and I didn't do it. I may want to repeat myself a little in lecture, or maybe not. This axis tilt has everything to do with seasons. And the reason why can be seen pretty quickly. So first of all, boy, I wish this picture was, here's a good picture. So I will probably start off today's lecture doing something like this, but giving you some formal notes on it. If you look at this picture, you can see that Earth maintains its 23.5 degree axis tilt in the sort of same, let's undo that, in the same orientation as it orbits around the sun. Meaning Earth is orbiting around the sun, but that 23.5 degree axis tilt it kind of keeps the same orientation, which in this slide is up and to the right. Because of this, Earth makes 4 key geometrical alignments with the sun at 4 points in its orbit. And let me change colors to kind of show you what's up there. This date here is called the spring equinox. And on the day of the spring equinox, I need you to kind of put on your 3D thinking caps here. The Earth is tilted, but it's tilted in such a way that the tilt makes a right angle with respect to the sun. And to see this, I might actually need to exit the share mode for a second and show you my globe. If you guys are the sun, if this little camera here is the sun, there is a single day in which Earth's equator points most directly towards the camera. And on that day, let's see if I can do this with my meter sticks here. On that day, although the Earth is tilted 23.5 degrees, the tilt is kind of perpendicular to the direction of the sun. And that's not true a day before or after. If you went a day before, the axis tilts, it's not quite perpendicular. It's basically the day of the spring equinox is when when Earth's equator is pointing directly towards the sun. This might be a little easier to see with one of the other geometrical alignments, like the day, for instance, the day of the summer solstice, right? On the day of the summer solstice, Earth is sort of moving through its orbit, and the summer solstice occurs when the North Pole is tilted most directly towards the sun.
Where's her excuse?
Hey, Chatty Cathy. Joey, you might want to mute yourself so that we don't have to compete with each other. Is that okay? Actually, I can fucking mute you. Hold on. Oh, who is this guy? Hey, 3567063. I'm muting you. Okay, maybe next time mute yourself. All right. Anyways, a day before the summer solstice, the North Pole does not quite point at the sun. And a day after the summer solstice, the North Pole does not quite point at the sun. But on the day of the summer solstice, that's the day that the North Pole points at the sun. That's a geometrical alignment. So let's look at that in my slideshow. I'll take some notes on this later on, but I'm trying to explain this question as I go, which is a little unfortunate. So this is the spring equinox. Here is the summer solstice. You can see the North Pole is tilted most directly towards the sun. This, of course, is the fall equinox. This configuration here is the winter solstice. That's the day when the South Pole is most directly pointed towards the sun. Those are 4 key geometrical alignments. Let me show you a picture of one of them and see if you can guess the day. Let's see if you're following me here. What day is this?
Winter.
Winter solstice. Very good, Whitney. How did you know that? Tell us how you knew that.
Because you just showed us.
I mean, that's kind of what I was thinking, but
Oh.
what visual cues?
I'm not sure.
You just know it's winter, but sometimes you can know a thing, but you can't explain why it is. I would have said, the way I would have done it, Whitney, is I would have said, I know this is the winter solstice because the South Pole is tilted towards the sun here, and the North Pole is tilted away from the sun. That's how I would have done it. Okay.
Gotcha.
If this had been the spring equinox or the fall equinox, the sunlight would be falling across Earth in this way equally for both hemispheres. All right. Anyways, okay, you knew it was the winter solstice, but describing it took a little bit of work.
Yeah.
I want you to imagine something. So we're going to get into light at a later time, but y'all know that light is a form of energy because when you step outside and you step into the sunlight, you feel warm. So you don't have to be convinced too hard of that. Imagine I had 2 flashlights each with an equal diameter beam of light. These flashlights would transmit an equal amount of light energy to the ground. On the left, we can see a flashlight which is perpendicular to the ground. Let me see if I can get my stupid taskbar out of the way. There we go. Okay. This flashlight on the left has a beam which is perpendicular to the ground, and the light falls here on that circle. This flashlight on the right, its beam is striking the ground at an oblique angle, at a glancing angle, and the energy is concentrated here in this oval. Which patch of ground rock would you expect to be warmer? The patch on the left or the patch on the right?
Left.
That's correct, Nina. And if you can try, why would the left patch end up being warmer than the right patch? How would we say that?
Because the light is like directly hitting it versus.
Okay, but why does direct versus indirect matter? That's what we're trying to get at.
Oh.
It's something about this versus this. It's not that you're wrong. It's that I want to explain why will this patch be hotter than that patch?
I'm not sure.
Whitney, do you have any good words for me? Joey?
No.
Well, you knew that this patch will be warmer, but you can't say why. My way of thinking, my way of explaining it would be each beam contains an equal amount of energy. So I know that the energy in the beams is the same, but the area that this beam falls over is smaller than the area that this oval beam falls over. So if you have the same amount of energy in a smaller area, this patch of ground will be warmer. What I wanted to hear is the sunlight is concentrated on a smaller patch of area. Okay, so that's fine. This is why we take a science class, so we can learn how to say and think like this, okay? Oh, hey, Alfred in the background had actually said that. I'm sorry, Alfred, I didn't see your chat until right now. Unmute yourself sometime, say hi to me, okay? But the chat thing is okay, it just, I don't always look at it immediately. Alfred understood me. Okay then, let's tiptoe back over here. Suppose I were to number these beams. 1, 2, 3, 4, 5, 6. Which beam would be most effectively heating up the ground rock underneath it on the day of the winter solstice? 1, 2, 3, 4, 5, 6. Which beam?
3.
6-1? Oh, wait.
3, says Nina, correctly. Well, okay, so Nina, talk to me. Why is 3 the most effective at heating up the ground rock?
It was actually Whitney who said 3.
Oh, I'm sorry, Whitney. Damn it, Whitney, why is it 3?
Oh, because it's like directly pointing.
Yeah, it's let's come up with some fancy vocabulary. It's perpendicular to the ground, but the light is most direct. I guess that's how you could say it. Direct is a bit more vague. Less vague is the beam of light is perpendicular to the ground rock in position 3, okay?
Okay.
So the area of Earth that must be warmest, the area of Earth that must be warmest on the winter solstice on December 21st would be a latitude of 23.5 degrees south, known as the Tropic of Capricorn. Huh. I guess when it's wintertime for us, it's summertime for people in Peru or Argentina, whatever. Okay. So what we've learned is that the seasons are actually being caused not by the changing distance from Earth, they're being caused by the axis tilt. It's a change that the angle of the sunlight makes on the different hemispheres of Earth. For instance, if we can use the camera once again, in the summertime, closer to the summer solstice, the northern hemisphere of Earth is tilted towards the sun, and so the rays of sunlight are beating down most perpendicular on the northern hemisphere. In the southern hemisphere, when it's wintertime, the rays of sunlight are most direct down here in Australia. Weirdly, if you live on the equator, if you live somewhere like Indonesia or what is it, the Congo, or if you're in, somewhere in Colombia, the days of the year that are closest to the warmest days of the year are actually the equinoxes. If you're in Colombia or if you're in Ecuador, the hottest day of the year is both spring 21st and March 21st, okay? And it's this axis tilt that's causing seasons. Let's imagine Earth didn't have an axis tilt. Let's imagine Earth was perpendicular to the ecliptic plane. In that case, it would be true that the equator was hotter than the poles because sunlight would strike more perpendicular on the equator and more oblique at the poles. But let's think about it. As Earth went around the sun, even though it was changing its position, there would always be the same relationship between the equator and the sunlight. It's that tilt and the different orientations that Earth makes with the sun that is responsible for seasons. All right, let's try to answer our question. If a new planet has a circular orbit and an axis tilt of 35 degrees, would we expect this planet to have seasons, yes or no? What's the answer?
Yes.
Alfred, was that you saying yes? I couldn't tell if that was background noise. It was like echoey. Could you say it again? I don't know if you got a wacky internet connection or what. What's the answer? Anyone, help me. Alfred's muted himself. He's scared now. What do you think, Nina? Someone's got to talk to me here. I'm going to sit down and take a nap. Would this planet have seasons?
Yes.
Yes.
Okay.
Because axis tilts are the cause of seasons, at least for circular orbits, okay? All right, so let's start writing down an answer. Write everything that I write in exactly the way that I write it. Yes. A planet with a circular orbit and an axis tilt of 35 degrees would have seasons. Full stop. Okay, would the seasons be more or less extreme than Earth's? Here I'm going to ask you to stretch your imaginations a bit. If I'm more tilted, will that exacerbate seasons or will that mitigate seasons?
More.
More, that's right. More tilt equals more seasons. You know what I think would be the most season-y planet I could imagine? The planet Uranus, for instance, happens to have an axis tilt of 97 degrees, which means it's almost perpendicular. Hey, that's right, Alfred, you wrote me. Alfred, that's cool that you're at work. We won't tell your boss if you don't. And we want you to get involved a little bit. So that's cool. And we don't mind if you pop it out. The only issue, Alfred, is when you talk to me, you sounded like a troll in a cave. It was like really, really echoey. And it was so echoey that I couldn't really hear what you're saying. So try anyways. Maybe you can figure out your microphone situation. But Zoom, let me tell you something, pal. Zoom is fun. It's easy to use. And, you're going to love it. Anyways, suppose you were the planet Uranus. If your axis tilt was 90 degrees, think about what a year, okay, first of all, an orbital period of Uranus is like 68 years or something. So if you're on Uranus and you're going around the sun, for half of your orbit, for 34 years, only the northern hemisphere of Uranus gets any sunlight at all, and the southern hemisphere is completely in darkness. And then eventually, as it goes around the sun, both hemispheres get a bit of sunlight, But then once it goes into winter time, only the southern hemisphere gets sunlight for 34 years. So for 30 years or so, this is getting really hot, and this is in complete cold darkness, and there's probably strong convection going back and forth. It's totally effing insane. Uranus has probably the most extreme seasons of any planet in our solar system. By the way, it's really fucking cold on Uranus because it's like 20 times farther from the sun, but seasons are not temperature, okay? Just because it's cold doesn't mean the seasons aren't extreme. Seasons are a change in temperature. They're not temperature itself, okay? Anyways. We expect this planet's seasons to be more extreme than Earth because its 35-degree tilt is greater than Earth's 23.5-degree tilt.
Can I ask a question?
Sure enough, yeah.
So is a 35-degree tilt like tilted further away than?
Hold on. I don't like when you use the word further
Okay.
because it implies distance. If you
Yes.
take a quick look at my slideshow again,
Yeah.
and let's back up to here.
Okay.
Whoops. The tilt is actually 23.5 degrees with respect to the perpendicular to the ecliptic. But sometimes saying all that is like too long, didn't read. It's like too many words.
Yeah.
And another way to look at it is the equator by geometry is also tilted 23.5 degrees.
Okay.
So if you're going from the North Pole, you would technically have to say 23.5 degrees with respect to the perpendicular of the ecliptic. But people just drop the perpendicular to the part because it's too much for people to handle. And since you're also tilting the equator 23.5 degrees, it's all within reference to the ecliptic plane that you're measuring this. So we just say 23.5 degrees with respect to the ecliptic plane, dropping the perpendicular. So I think that's kind of the question you were asking, right? But I didn't like when you said further, because when you start saying further, I start thinking distance from the sun, and now I'm muddying all the waters and it's messy.
Yeah.
So what were you trying to say?
I guess I'm just trying to imagine, I don't know, this is a little confusing for me. I'm just trying to imagine like what the tilt, like, I guess like looks like, and I can't really imagine what 35 degrees versus like 23.5 degrees.
Oh, good question. Okay, so let's, I'm going to use the whiteboard feature here.
Okay.
And this is what I think it would be like. So let's say that's the ecliptic plane.
Mm-hmm.
And let's, oh, this is fun to play with shapes. Let's draw a couple of different planets. Let's make these yellow planets, okay? So here's one planet, and we'll make the other planet lime green, okay? Let's make the lime green planet Earth. So with 23.5 degrees, geez, I could bust out my protractor here. It would be cool if, okay, I'm gonna do a quick little thing here, these black lines. All right, so here's the perpendicular, here's the ecliptic, and using my best geometry know-how, half is 45. I'd say, let me undo that. I'd say while this is like a 23.5 degree angle, I would say, let's make a perpendicular to the ecliptic here. I would say this is a 35 degree angle. Okay? So
Okay.
the angle is a bit more tilted from the ecliptic. So you see what I'm saying? So this would be 23.5, and this would be the more extreme 35. It's getting closer to halfway, because remember, this is 90 degrees, right? So halfway is a 45-degree angle. 35 is a bit closer.
So the larger the tilt, the more extreme the seasons would be.
That's correct. But we still have one job left to do before this problem is done. How do we explain why in a simple one-sentence answer? Why does more tilt equal more seasons? What did we learn? If a little kid says, why do tilted planets have more extreme seasons? What do we tell them is the answer? Whitney, can you tell me?
Hey, sorry, what was the question?
The question is why? Why does more tilt equal more seasons? We just need one sentence to get our fifth point here. One sentence that explains why is the tilt causing the seasons? It's basically related to the stuff we just learned. I'll give you a hint, all right? Why does more tilt equal more seasons? It has something to do with this picture.
Because you would get more of those, whatever those yellow arrows mean.
What are
Sun
these
rays.
yellow arrows? What are those yellow arrows?
Sun rays.
Okay,
See-
good. Those
Oh.
are rays of light from the sun. So
Okay.
what's changing with tilt? We're changing the, how do we say this? We're changing the sun rays,
Are you asking me?
I'm asking anyone. So
Oh.
the exercise that we're trying to do here, Whitney, is it turns out it's pretty fucking hard to explain things. And
Yeah.
right? And I understand that, but the way you get better is by flexing that muscle a bit. So I want you to try, even if it doesn't come out so good. I want you to try to explain what is changing with the sun's rays when we're changing that axis tilt.
We got more of them?
No, you get the same amount. The area of Earth doesn't change. You're still getting hit with 1, 2, 3, 4, 5, 6 rays. So you're not changing the quantity of sunlight. You're changing something else.
Like
Like
more, oh, sorry.
Sorry, I didn't mean to interrupt you.
Anyone,
Whitney.
go ahead,
I
interrupt.
was gonna say more of Earth is maybe getting covered because of the degree.
Nope, the
Like-
same amount of Earth is being covered.
Okay.
One half of its body or its diameter. Yeah.
Like a focus area almost.
Focus is the wrong word to use here. I'm looking for a much simpler word that relates to this ray striking Earth in this way. What's changing here?
That's not the direction of
It's not the direction. You're getting closer now. You're getting, shall we say, warmer?
Equator.
Not the equator.
Oh,
All right. Okay, look. I'm just going to tell you, okay? Because I don't want to
Okay.
beat this. You're changing the angle of the sunlight. I wanted to hear angle of the sunlight. When Earth let's look at that thing we drew together. When Earth, where's that damn whiteboard? This is a good use of the whiteboard today. Let's met the orange rays. When you change the tilt of Earth, you're changing the angle. The angle that the sun rays make with Earth will change more extreme over the course of the year, right? Let's just think about Earth versus Uranus. In Earth, you're changing the angle of the sunlight from beating down like this to sort of hitting like this, right? On Uranus, they're all coming down on the top or the sides, right? So it's top down versus sides. Earth is tilted a little bit. It kind of hits like this versus the side. And if Earth had no tilt, you know, the planet Jupiter doesn't really have seasons. Jupiter has no axis tilt whatsoever. So the angle that the sunlight makes with the different latitudes is always the same. And Jupiter might be going around the sun, but it doesn't really matter because the sunlight is always perpendicular to the equator and glancing at the poles. All right, anyways, there is a reason why I'm doing these homework problems with you, okay? It's one, so that you can practice talk and write, but two, so that you end up with the right answer and learn something good. The correct answer is, this is because a more extreme tilt will lead to a greater variation in the angle of sunlight over the course of one orbit. Variation in the angle of sunlight. Let's underline that. Whew. All right. Well, that first one was a bit of a doozy, but I knew that was going to suck because I didn't really talk about it in our first lecture. So part of that is bad on me, okay?
For these homeworks, do you want us to like write them out on like notebook paper or type them up or anything?
I'd actually prefer you write them on notebook paper because most of you do not have the skills to type it in such a way that will please me. If
Okay.
you are going to dare type this up, you better make it look really effing good. Like, it better look awesome. And especially when the math stuff is concerned, I want it formatted nice. Hell, I even want your font choice to be good. Unless you really are a master of graphic design, and unless you can handle an equation editor, I think it would be simpler for all of us if you just write it. By the way, Nina, one of the
Yes.
reasons I do these homeworks with you is because later on you're going to have a perfect fucking study guide. You're going to be able to look at these questions and see the most perfect answer, and then you can study from that. So if I were a student, I would probably actually, since we're not, normally you would put this on a piece of paper and staple it and turn it into me. But since we don't have to do that, since all you need to do is a photograph, I would actually keep it in my astronomy notebook. And then as I went through, I would have my notes for that week, and then I would have the homework for that week in the lab for that week, and then I wouldn't lose any of the papers. And if ever a dispute came up, which is, whoa, did you turn in homework number 2? You would have it all right there. So that's,
Yeah.
I think you should keep it in your notebook. You should put your name in homework 1 so that we see where homework 1 begins and ends. And then you're going to photograph all these 5 pages or whatever it takes, and you're going to submit those.
Okay.
Sound good?
Yeah.
All right. That was actually a useful question. I would like to erase this. Can I erase this? Whitney, Nina, Alfred, Joey.
Yes.
Yes.
All right, here I go. One last time for the people in the back, okay? All right. All right. 1 down, 4 to go. Nina, if you can, I'd like you to read me chapter 2, number 48.
Sure. Let me number 48.
Yep.
Okay. A farther moon. Suppose the distance to the moon were twice its actual size or actual value, excuse me. Would it still be possible to have a total solar eclipse? Why or why not?
Okay. Man, I think all of these questions are about stuff that I did not quite get to. This is a little bit about angular size here. Let me, I'm annoyed with myself. All the things that I told you last class were useful things to tell you at the beginning, but I don't think I hit one of these damn questions. I didn't quite get to them. I took too much time. All right, so by the way, I don't know if you guys know this, but there was a total lunar eclipse that happened this morning. The problem is you couldn't really see it from Rhode Island because it started when the moon was just setting on the horizon. And there are different types of lunar eclipses, okay? So let me show you a couple of slides here, and then we'll kind of get into the answer to that question. One of today's big lessons, one of the important lessons that I have to teach you at the start of today's class is that when you look at an object in your sky, you don't see it as like, you don't see its true size. You see it as an angle. And this is actually not only true for astronomy stuff, it's actually true for even looking at things in a classroom or looking at your friends when you're out at a dinner table or something. You see angles, you don't see sizes. For instance, the moon is a big giant sphere whose diameter is 3,400 kilometers. But you don't see something in terms of kilometers. When you look at it with your eyeball, you see it as an angle. So we need to have a big old discussion about angles. And in fact, the rest of today's homework is all about angles. And unfortunately, angles are what I didn't get to at all because I was just about to get to it when time ran out. So that's a little bit unfortunate. There are also different types of eclipses, and I'll probably defer a proper discussion of eclipses until a later time because I've got a lot of stuff to teach you in the beginning. But let's take a quick peek at lunar eclipses. So here's a little setup of the way today's eclipse looked like, function F591. A lunar eclipse happens when the moon is on the other side of Earth from the sun, but the orbits align in such a way where where the moon is directly behind Earth and in its shadow. So here we have the sun, we have Earth. You can see that the Earth gives off two types of shadows. This really dark shadow is called the umbra, and this half partial shadow is called the penumbra. Up here, there's no shadow at all. So if the moon was over here, you could see it and you could see all the reflected light from it. Here, the moon gets a little bit darker. If the moon is there, you see a partial lunar eclipse. And in today's case, for a short time, the moon passed through the umbral shadow of Earth, and then you could see a total lunar eclipse. Unfortunately, the total lunar eclipse was best viewed from like California or beyond. We were kind of not in the right position on Earth. Basically, when the eclipse started, Rhode Island was like here. So, and it was rotating into daylight, so it wasn't ideal. In any case, the way these eclipses look are different, all right? So in a penumbral lunar eclipse, the moon gets just a little bit darker. I'm sorry, why am I talking about lunar eclipses? Didn't this question ask about solar eclipses? I just realized that. Okay, let's try this a different way. Okay, man, I'm such a stupid idiot today. Okay, let's talk about solar eclipses instead. Here's solar eclipses. When the moon is on the other side, let me see if I can find that same set of diagrams. Solar eclipse diagram. Yeah, here we go. This is a picture. I need this. I need to steal this before it disappears from the internet. Save image as, and bear with me, guys. I'm sort of multitasking here. Pics. Solar eclipse. Okay, cool. All right. I'm sorry, I forgot that the question was asking about solar eclipses. During a solar eclipse, the moon blocks the sun. So you have sun, you have moon, and you have Earth. Just like the Earth gives off two types of shadows, the moon gives off two types of shadows. A dark umbral shadow seen here, and a semi-partial shadow called the penumbral shadow. And both the umbral shadow and the penumbral shadow kind of appear on Earth. In fact, in this picture, you can actually see the two types of shadows as seen from the International Space Station. Check out slide 96 here. Here you can see the umbral shadow, right? And you can see there's kind of a partial shadow, a partial ring around it. That's the penumbral shadow. And you see a different type of eclipse depending on whether you are in the umbral shadow or the penumbral shadow. And this is what they look like. You can see a partial solar eclipse if you're in the partial shadow, and that's where you block some of the sun. A total solar eclipse is when the disk of the moon perfectly covers the disk of the sun. Now, the moon's orbit is not a perfect circle. So sometimes when you get just the right set of conditions, you can get a total solar eclipse when the moon is a little bit farther away from Earth. And when that happens, you get a very magical type of an eclipse. It's called an annular solar eclipse. This word annulus is Latin for ring. And they sometimes call it the ring of fire because you're blocking out most of the sun, but a little piece of the sun's surface is illuminated all the way around the moon, and you kind of see this glowing ring in the sky. Honestly, some of the pictures of annular eclipses are just so cool and wild. People make a cottage industry of trying to take pictures of annular solar eclipses in front of famous monuments like the Taj Mahal or something. So look, here's someone taking one over some groovy plain. Let's see. All right, here. Well, that's not quite a full annular eclipse. Here's one over a couple of oil derricks in Texas. I find this one to be particularly pleasing. If you look up at the sky and you see that happening, shit looks fucked up. It looks weird, right? That's like something very impressive. So annular eclipses are kind of a beautiful thing to behold. Now, it turns out that most of the things that you see in your field of vision, you're seeing them as angles, right? And it turns out that the angular size of the moon, I'm spoiling my entire lecture today, so I'm really irritated about this. The angular size of the moon is roughly half a degree. And as a kind of rough measurement tool, you can use your hand as a sort of angular measurement tool. If you hold your finger out at arm's length, your finger subtends 1 degree. So next time you see the moon, probably not the sun because you'll hurt your eyes, but we're roughly in a full moon right now. So if it's clear tonight, go out at night, and next time you see the moon, I challenge you to hold your outstretched finger against the moon, and you will discover that the moon is basically on the sky is half the width of your finger. It doesn't seem like it's going to be like that, but go ahead and find out for yourself. The moon is about half a degree. So in this question, they're trying to ask us, what would it be like if the moon wasn't just changing its distance by a little bit? What would happen if the moon was twice as far away from the Earth? So what if the moon was like over here? And the question they're trying to ask us is, do you think you would still be able to have a total solar eclipse? And remember, the total solar eclipse looks like this. What do you think the answer is? I know we're learning this on the fly, so it's not entirely fair, but try to answer it anyways. Do you think you could have a total solar eclipse if the moon was 2 times farther from Earth?
No.
No.
Yeah, no.
And that's because it would be a more extreme version of an annular eclipse. If the moon was twice as far, so I guess the thing that we didn't talk about is when things are farther away, their angular size shrinks, right? The farther, actually, you can kind of demonstrate it, right? Look, I mean, here's Moonball, right? The camera that you watch this video on also sees angles. Now, I happen to know that Moonball here has a diameter of maybe 5 to 6 centimeters or something. But who cares that its diameter is 5 or 6 centimeters? As far as your camera is concerned, it's an angle. When I put this right up in front of the camera, it has a large angle and it blocks my face and it blocks the whiteboard. As I move Moonball farther and farther away from the camera, the angular size that it subtends in your field of view is smaller and smaller. And you can actually measure this in degrees. One of the things that astronomers, one thing that I have to do when I'm taking images on the sky, I have to consider what is the angular size of this moon or planet or star in terms of my camera. So cameras see angles just like your eyeball does. Here, the angular size is big. If the moon's farther away, the angular size is small, and then you cannot cover the disk of the sun because the sun is this fixed distance away from you. So let's go ahead and just answer this question and put it behind us. If the moon were twice as far as it is today, then no, a total solar eclipse is not possible. The way we want to talk about this is in terms of the key phrase angular size. This is because the angular size of the moon would be reduced. I want you to underline the phrase angular size because that's a key idea. This is because the angular size of the moon would be reduced probably by half and no longer cover the disk of the sun. Now, it is true that you would get something like an annular eclipse. In fact, let's just for fun draw what it would look like. It would probably look something like this. And that's a more extreme version of an annular eclipse. And you can even draw that picture here. This is the moon. This is the sun.
Does that say cover the disk?
That's right. Cover the disk. When you see the sun or the moon on the sky, they are a disk to your eye's perspective. You can even draw that little picture there so that you remember what the hell we're talking about. All right. Well, this homework is going as predictably bad as I thought it would be. It's all of these subjects I was just about to get to. I just went a little too slow, and unfortunately, I'm paying the price for it. I shouldn't have taken quite so much time on that background stuff. One thing that I am going to be glad for, the next problems are more mathematical, and I taught you guys that dimensional analysis technique last time. That's going to be quite helpful. All right, Whitney, we're back to you. Let's go ahead and erase this. Can I erase?
Yes.
All right. Whitney, chapter 2, 53.
All right. Arc minutes and arc seconds is the title.
Yep.
All right. There are 360 degrees in a full circle. A, how many arc minutes are in a full circle? B, how many arc seconds are in a full circle? And C, the moon's angular size is about half the degree.
Half a degree.
Okay. What is this in arc minutes and arc seconds?
Okay. Arc minutes and arc seconds will be covered in today's lecture. I actually thought about doing this homework after lecture, but I kind of have set times for things and I didn't want to mess with it. Let's look at some pictures so that we understand. When I was in high school, I had to take a geometry class, but I don't think that's a popular thing anymore. I think people like skip geometry. I'm old, so. But there was something nice about taking geometry. You learn a little bit about it. Of course, when you're in high school, you don't appreciate it, but later on you do. Degrees are a unit of angle invented by the Greeks. And let's see what they did. They took a circle, they divided the circle into 360 little pizza wedges, And each one of those little pizza wedges was 1 degree. When you look at 1 degree on a circle on a piece of paper, a degree looks like a really tiny angle. And so probably the Greeks thought this was a good enough way to break up circles. What's different is in astronomy, the circle is your sky, or rather your sky is kind of like half a circle. And the sky is so far away that it's effectively at infinity. And when you look up at the sky is so big that degrees actually become not a small angle, but a big clumsy angle. Now, it might not seem to you like your outstretched finger is a very big wedge. It's basically your finger is 1/80th of the dome of the sky because it's 1 degree and the sky is about 180 degrees. But it turns out that the moon and the sun, like coinky dinky for no reason whatsoever, the moon and the sun are both roughly half a degree in terms of their angular size. I can't really draw this on the board, so I'm going to do this over here. So in other words, if you take your outstretched finger and you hold it up towards the moon, you'll discover that the moon is roughly half the width of your finger, and so is the sun. So the angular size of the sun and the angular size of the moon are both half a degree. Now think about it. The sun and the moon are the 2 largest astronomical objects that you could look at. Everything after the sun and the moon is either a star or a planet, and they are microscopic in terms of their angular size. For this reason, astronomers need even smaller angles that you've probably never heard about. Introducing the arc minute and the arc second, okay? Now, the way you make an arc minute, it's kind of the same relationship between an hour. It basically treats a degree almost like an hour. You take a degree and you zoom in on it and you blow it up, and then you cut that degree into 60 more wedges. And each of those little tiny pizza slices is an arc minute. The abbreviation for an arc minute universally is just to put a single apostrophe after your 1. An arc minute is equivalent to trying to look at a soccer ball from a half a mile away. It's a pretty tiny angle. And then astronomers invented an even smaller angle called the arc second. That's where you blow up an arc minute, and once again, you divide the arc minute up into 60 more wedges. The universal symbol for an arc second is sort of a 1 with 2 apostrophes behind it. I think that the way we should treat this problem, since we did have a little lesson on dimensional analysis, is we should treat this from the perspective of a conversion factor. And here are the 2 conversion factors that we are going to use, okay? The first conversion factor is that 1 degree is equal to 60 arc minutes. I want you to write that on the side of your page and put a box around it. Degrees to arc minutes. The other conversion factor is 1 arc minute is equal to 60 arc seconds. You will remember that in our previous lecture, one thing that I did do right is I taught you the skill of dimensional analysis. And in this problem, we are going to use the technique of dimensional analysis to convert 1 circle into arc minutes. I volunteer Nina for the job because she's looking like she's dying to volunteer. Okay, so Nina, here's what you're going to do to work us through this problem, okay?
Okay.
I want you to go to your 4 steps of dimensional analysis, which is in your notebook, correct?
Yes, I have it.
Awesome. Okay, so why don't you, so just so that we don't have to get too stressed out about this, I would like you to just sort of read to me the first step in dimensional analysis. What is that?
Sure. Is it write down the number to convert with its units?
Correct. Okay, so here I'm trying to find out the number of arc minutes in 1 circle. What should I write down?
60 arc minutes.
60 arc minutes is part of our conversion factor, but 60 arc minutes is not what we are being asked to convert. What are we being asked to convert? That's part of the,
One,
yeah, pardon?
one circle.
Okay, fine. We could actually treat circles as a unit, all right?
Okay.
And we could even write down one circle. Fine. What's step 2 of dimensional analysis?
Multiply by a division bar.
Okay, that's not too hard. What's step 3?
Put the units in first to cancel out.
Okay, so I need to put some unit on the bottom and some unit on the top. What unit should I put on the bottom?
Circle.
That's right. I need to cancel out the unit that is circle. Okay, that part was good. The question now is, what do you want to convert circles into?
Arc minutes.
That is true, but you have a problem, Nina.
Okay.
The problem is that you don't have a conversion from arc minutes to circles. You have a conversion from arc minutes to degrees. That suggests to me that we're going to have to do a 2-step dimensional analysis.
Okay.
We should first convert circles to,
Degrees.
okay, fine. Now, we can either proceed to step 4 and put our numbers in, but you know what I like to do, Nina? I like to do out all of the division bars with all of the units and put the numbers in last. I think that's a classy way to behave.
Okay.
So let's go back to step 2 and let's put in another division bar. And now we're going to go to step 3 again, which is put your units in first. Why don't you tell me what units I should put in?
Degrees.
Where did degrees go? Top or bottom?
Bottom.
That's right, because degrees are currently at the top. And what do you want to convert your degrees into?
Arc minutes.
Correct.
Yes.
Yes,
Okay.
because we're looking for the number of arc minutes in one circle. And by the way, you do have a conversion from degrees to arc minutes, so that's cool.
Okay.
All right. Now we have to proceed to step 4. What is step 4?
Put the numbers in second using conversion factors.
All right, so now we have to use things like this to put numbers in top and bottom. So what number do I put here?
1.
No.
No. 60?
Pardon?
60?
No. This is a conversion factor from degrees to circles. How many degrees equals how many circles? What is the conversion factor from degrees to circles?
1 equals 60? No, am I getting this wrong?
You are getting this wrong.
Okay, I'm a little confused.
Basically, we need to know how many degrees are in a circle.
Yeah. Oh, 360.
Right.
Yeah.
There's your conversion factor. We didn't
There it
write it this way, but that's still a conversion factor of sorts. So try again.
Yeah.
What number goes top and bottom?
360 goes on the top.
360
And-
degrees is equal to,
1 circle.
that's good. Okay. Now do the same thing over here.
Okay. 60 goes on the top.
60 arc minutes.
Arc minutes goes over 360 degrees.
Wait,
1 degree.
1 degree is equal to 60 arc minutes, right? That's what goes in these division bars are conversion factors. You see what I'm saying?
Yeah.
You fixed yourself.
Okay.
60 arc minutes is equal to 1 degree. Okay, now we're ready to solve the problem. It looks like we have to take 1, multiply it by 360, divide by 1, times it by 60, and divide by 1. Forget all the ones. What we really have to do is 360 times 60. So do that on your calculators now and tell me what you get.
21,600.
And what are the units?
Uh,
No.
degree.
No.
No.
Degrees have canceled out.
The degrees are canceled out, so arc minutes.
That's right. I'm going to put my conversion factors a little smaller and higher up. I don't like the way they're getting smushed into my answer here. So hold on a sec. So our answer is 21,600 arc minutes. So we have 1 degree is equal to 60 arc minutes. And we have 1 arc minute is equal to 60 arc seconds. Okay. That's part A. By the way, when problems have a part A and a part B and part C, I want us to label them as such. That way the grader knows what the shit is going on. Whitney, what's part B ask? I already forgot.
How many arc seconds are in a full circle?
Okay, there's actually a couple of different ways to do this problem. Nina, because you just did the previous problem and you probably learned something, what do you think is the most efficient way to do this? Or what way appeals to you?
How many arc seconds are in one circle? Is it by the same?
We always
format?
want to use dimensional analysis. It's
Yeah.
just what do we start with that matters here.
I'm confused by what you mean by like, what do we start with?
I mean, we could start with one circle, we could start with 360 degrees, or we could start with 21,600 arc minutes. What do you want to start with?
Probably the 21,600 arc.
That's what I was thinking too.
Yeah.
So let's begin with 21,600 arc minutes. All right. Let's begin by writing down 21,600 arc minutes. That's step 1 of dimensional analysis. What is step 2?
Multiply by the division bar. Or by division.
What's step 3?
Put the units in first. To
That's a
cancel
you job. Tell me what units go top and bottom.
out. Arc minutes goes in the bottom. And arc seconds, no, degrees go on the top.
Wait, do I want to convert to degrees? What is the question
No.
asking? You got to think about what you,
So arc seconds goes on the top.
because that's what we would like to end up with, because that's what the question asks. Okay, that's step 3 of dimensional analysis. Notice that your arc minutes cancel out. Good. All right, what's step 4 of dimensional analysis?
Put the numbers in second. So
All right.
So we're putting 360 on the bottom.
Wait a
No. I'm
You need to use, remember what the words say. Put the
Yeah.
numbers in second using conversion factors. You need to use a conversion factor there. What's your conversion factor from arc seconds to arc minutes?
It is, or do you mean arc minutes to arc seconds?
Yeah.
Okay, so 1 arc minute equals 60 arc seconds. So 60 would be on the top and 1 would be on the bottom.
That's how you do it. You have to use your conversion factors. This is your conversion factor. 60 arc seconds is equal to 1 arc minute. Okay, looks like you got to multiply those two. Do that, both of you, and tell me what you get. And by the way, if you're watching this video at home later, you better be punching into your calculators too, or I hate you.
So the answer is 129.
Careful.
Oh,
Say it
one,
better.
sorry, 1,296,000.
Don't we have a
Arc.
rule about
Yes, we do. Rule.
what's the
We
rule?
do. It is, I'm forgetting the name of the rule, but it's putting it in a scientific notation.
Beautiful. Why don't you exercise your skills, Nina, and help me put
Yes.
that into scientific notation? We can keep all the significant figures, by the way, and I can explain that later.
So is it 1.2 times 10?
Keep
Okay.
all the significant figures here.
Okay,
1.296.
1.296.
That's right. By the way, if you were going to stop there, you better make that 1.3 if it's 1.29. 29 cents is closer to 30 cents. But anyways, in this case, we're going to keep all significant figures. 1.296 times 10 to the what?
The 6th power.
And what are the units?
Arc seconds.
All right, don't be sloppy in your handwriting. Do not make it look like to the power of 611. Make sure you differentiate those as arc seconds. Box it because that's a classy move. 1.296 million arc seconds are in a circle. By the way, I'd like to have a discussion for any advanced students out there that might be watching later. Why did I keep all of these significant figures? These conversion factors are perfect conversion factors. They have infinite precision. We define there to be exactly 60 arc minutes in 1 degree. We define there to be exactly 60 arc seconds in 1 arc minute. And we define there to be exactly, perfectly, precisely 360 degrees in 1 circle. That means there are truly 1,296,000 arc seconds in a circle. Ask me about that some other time if you want. Okay, Whitney, why don't you read us part C and we'll have you try part C. Do you guys have this? Because I think I need, no, I'll try to keep it all in one thing. What's part C ask us to do, Whitney?
The moon's angular size is about 1/2 degree. What is this in arc minutes and in arc seconds?
Okay, how do you want to go about this, Whitney?
Do half of 60.
Okay, fine, yes. But I'm trying to get you to think in a different way. So you already knew how to do that. I'm trying to get you to rearrange your brain fundamentally to solve problems using dimensional analysis. So
Okay, yeah.
it's a little annoying in this case because you had the right idea, but just do it my way, okay? I promise you, you won't regret it.
Okay. I'm just looking for the first step.
Yeah, let's go do that. We want to start.
Oh, here it is.
Yep.
Write down the numbers to convert with its units.
Boom, 1/2 degree. I did that.
Oh, there it is. Okay, moon. Thank you. All right. And then then we'll put 60 at the bottom.
Whoa.
I mean, I didn't mean to say that. I meant sorry. The units is
follow the steps in order. Don't get creative. Don't get creative, Whitney. Creativity is bad, okay? Just follow the rules. That's step 1. What's step 2?
sorry, I don't think creativity is that bad, but all right, step 2.
Actually, well,
Multiply. All right, multiply by a division bar.
all right, there we go.
Oh, yeah.
Whitney, in my class, creativity is bad until such time as we say otherwise. Okay, so I don't want you getting creative on me, all right? All right, so there's step 2. What's step 3?
Put the units in first to cancel out.
All right, I need a unit top and I need a unit bottom.
All right, the unit top is 60 arc minutes.
No. Did I give you permission to get creative? What are you doing playing with numbers on me? Do you love math that much that you're dying to talk to me about the number 60? I gave you permission to put units, not numbers.
All right.
Try again. I need units, top and bottom, and only units.
It's just stressful, like trying to be a astronomer in one day.
Well, yes, but it's not stressful because we're talking about it and we're learning. You got to think about this in a different way, Whitney. You are learning a new skill. I am teaching you a new skill. So just play along with me and you're going to learn something. All right, units, top and bottom. What do I got?
So 60.
Wait. All right, slow your roll here. No numbers.
Oh,
Let's
one,
talk about, no,
1/2 a unit. Oh,
no. Units are the little tags that come after the number. The current units that you have are degrees on the top. I want to have a unit, top and bottom, and I'm trying to get to units of arc minutes.
I got you. Sorry. All right. So the 2 little lines.
That's arc seconds.
Oh, 1 minute, of course.
Okay.
Arc.
So what unit should I put on top?
The arc minute.
Yes. And what unit should I put on the bottom?
The degree.
Good. Now we understand each other. Hey,
Sorry, yeah.
someone's
I was
fighting.
trying to be creative.
Who's fighting with their dogs there? Oh, is that you? Oh, that must be in the background of your house. Okay, no big deal. Look, Whitney.
I don't have any dogs. That's not
Oh.
me.
I hid the trolls. Okay, whoever that was, fight your dogs on mute, okay? Whatever you're doing there, hide the non-video participant. Okay, Whitney,
Alright.
I think now we understand each other, correct?
Yes.
I
yes.
wanted to go, now, why did we put the units of degrees in the bottom? So that they will cancel.
So we can cancel them.
Boom, boom, okay. Now, what's step 4?
Oh, put the numbers in second using conversion factor.
I know you love the numbers because you were dying to talk to me about numbers. So let's get some numbers top and bottom using your conversion factors.
All right, so we'll do 60 arc minute at the top.
Yep. And what goes at the bottom?
1 degree.
Very good. And now we're going to basically do what you said to do 5 minutes ago. We're going to take half of 60, right? And what's the answer to that?
30.
All right. The real question, and let's put a box around that, 30 arc minutes. That's a classy move. The real question, Whitney, is not, can you divide by 60? I already know you could do that. And if
Thank
that was all it took to be an astronomer, well, then you wouldn't need to pay me $500. This technique is going to make you more powerful, and you will see this with time. That's why you must learn it. Okay.
Right.
That's only one half of the problem. They want the number of arc minutes, but they also want, Whitney.
Oh, arc seconds.
Okay, so what are we going to do about that in dimensional analysis?
We're gonna do the same thing we just did, but
That's
with
right.
second.
All right, so tell me what to do.
So we're gonna do 0.5 degrees.
We could
Times.
start there, and we could do this again. We could also
right.
start with the 30 arc minutes, right? That's kind
Oh,
of
yeah,
might as well, right? Okay.
yeah,
So 30 arc minutes, and then what? That's how we start.
times.
Division bar. Give me some units.
Oh, 30.
Oh, no. 30 arc minutes is
Right.
where we began.
Yeah.
Let's go through the steps. We have to do this by the numbers.
I put the 60 arc seconds at that time.
No.
Oh.
You are not allowed to talk to me about numbers until your units are in place.
Oh, yes, I forgot. Yeah, you're right.
All right,
We have to put the arc minute at the other bottom to cancel out.
Okay, what goes at the top?
The seconds, arc seconds.
Very good. Okay. And now you can give me those precious numbers.
Oh, 60 arc seconds over 60. I mean, over 1.
Right. 1
Right.
arc minute is
Yeah.
equal to 60 arc seconds. Okay. Punch that into your calculator or do it in your head, whatever you can do.
Oh, so 30 times 60?
Yeah.
Oh, 1800.
And the units? 1800 what?
Oh, arc seconds.
Very good. All right. That's our third problem.
Do we still have to submit this?
Yes, you're going to have to take a photo and submit all these questions to me.
All right, maybe I'll have to rewrite it.
Why? Are you not writing this nice or?
Like, I don't know. Maybe
Did you decide to write it on all these random scraps of
like I
paper?
have like I did what we were doing, but like sometimes I put little like a note in the corner over there about stuff.
I don't mind.
Oh, okay.
And wait, let me see what it looks like. Hold on, let me full screen you.
It says like Earth 300.
Just hold it up. Hold it up. I'll tell you if I like it or I don't.
My handwriting's really bad. I'm so sorry.
I've seen worse. I can
All
deal
right.
with that. Did you number them? I mean, it's a little all over the place, but
Yeah, I'll redo it. All right.
don't do it for my sake. Like
I just
Whitney,
didn't want you to, because you said yesterday, our Monday, you said like if it's sloppy, you're just gonna grade it wrong.
well, okay. If it's so sloppy that I cannot follow or read it, do you
Okay.
see how? Now look, I don't claim to have the neatest handwriting, Whitney, but look how I'm doing things on the board here. Wait, let me wait. Sorry, I want to unpin you. Remove pin. Okay. Do you see how? On mine, you can see, okay, chapter 2, number 53, this is part A, this is part B.
Yeah.
Now, I don't mind if there's notes and stuff in there, and I don't mind if it's messy, but there
Okay.
does get to a point where it's so jumbled that I can't even tell where one problem begins and another problem ends.
I put A, B, and C.
Then why don't you assume it's cool? Also,
All right.
because you're one of the few people who are interacting with me personally, you get a little mulligan for that. And I'll be
Right.
like, oh, it's Whitney. I know Whitney. That's cool.
You know
Now, those
that she
other
can really-
mother effers out there who are watching this later,
The other trolls.
yeah, all those trolls are going to have to work a little harder, okay? But that didn't look so terrible. Trust me, I've seen worse, okay? I've seen
Right,
worse.
thank you.
But in the future, going forward, you could work to make it a little bit neater for
I'm
yourself.
going to.
Yeah, remember, this will be a cool study guide for you come test time. Okay.
Okay.
That's number 53 down. Is everyone got this here? ABC?
Yeah.
All right. Let me
Yes.
check how we're doing on time because I got kind of lost in the sauce here. 11:40. We got 20 minutes to do 2 problems. I think that's doable. If not, we
59
could.
looks pretty long.
Huh?
59 looks pretty long.
Yeah, I'm a little scared about 59 myself, but maybe.
Yeah, and the next class starts at 12, so like we're not even gonna have a tea time.
Well, we can have a little break. I always give you guys a little break between, say, office hours and lecture. I'll give you a little tea break in the middle of lecture because it's 3 hours long. And then I sometimes give a little break between lecture and lab. Sometimes I just want to get it done. We'll see how we feel. We can talk about it. We can horse trade here. I will give us a little pause before we start lecture, I promise. Maybe a quick one, all right? Let's just crank out the next one. Okay, so this homework is sucking because, well, I just didn't get to any of the stuff that we needed. Anyways, so that's part of the reason why this is not too much fun. The next problem involves a formula. In fact, we'll see how we do. Let's see how long this, let's see how long this problem takes. It may be that I cut 59 out of this homework, just this once, okay? Yeah, Whitney's like, that sounds like a good idea. All right, so maybe because I didn't quite get to all this stuff. The thing is, I want us to do 59 at some point. I'm gonna have to think about how I want that to go. All right, fine. We're gonna remove 59 from today's problem set for sanity, okay? Normally, I want us to do 5 problems a class. Just this once, because I didn't quite get to all the material, we're going to do 4 problems, okay? Does that sound okay to you, Whitney? Does that sound okay to you, Nina? All right, so let it be known, I have henceforth struck 59 from today's homework. And in fact, before I forget, share screen. Let's do this right now. Let's go to homework number 1, edit. And let's put 59. Let's use strike through. Oh, can I do this? Strike through. Does that work? Yes. Can I use strike through up here? Whatever. Get rid of it. And we'll make a note. Off strike through. Sorry, this is weird. 59 removed from today's homework. All right. That way people watching later will know what the deal is. All right, that ought to help us a little bit. Now, with that in mind, I want to do a little something with 57 to make it right. Each class, you are going to learn a new formula from me. It is a formula that is essential to understanding how astronomers think. Before we do 57, you're going to set this up with me. Okay. Before I have Nina read us 57, I want you to do something. 57 is about using a formula called the small angle formula.
Should we include these notes on the homework sheet?
I think you should, because I just think you should. I won't explain why. So the small angle formula is a relationship between three quantities. Okay, let's draw a little diagram together. Over here, I'm going to have an
Oh
astronomical.
my God, I love saxes.
Really? I just
Yeah.
looked at it for the first time and it blew my goddamn
Did
mind.
you get a steak and cheese?
Oh, you know I did. I got mushrooms and peppers and onions. Dude, I even got the swag. I got the Frisbee. I got the little cooler. I got my second vaccine, my Pfizer vaccine. And I was like, oh yeah, going to Saks, gonna eat a steak and cheese.
Yum.
It was so good. All right.
I love saxes.
That's great. That's great. I've been driving past it for years and being like, I bet that place is fucking awesome. All I like are dirty hole in the walls that serve like some kind of local authentic food. That's the best.
Go to Julian's for breakfast. All right, I'm done.
Yeah, I know those people. Julian's are friends of mine.
Really? I know Julian too. I went there this morning.
Oh, really? Yeah, Brian
Yeah,
Oakley's an old friend. All of those people are old friends of mine. So we might have some similar circles. That's Rhode Island for you, right? We have to talk about that. All right, so on the right side of your page, draw an astronomical object like the sun, and let's put a line through it representing the diameter. Now, this could be the sun, the moon, a planet, any old astronomical object. You are an observer on Earth. We'll represent you with a little eyeball, and you're looking at the sun, and the sun subtends some angle in your sky, which we happen to know is pretty close to 1/2 degree. Bada boom. And bada boom. Okay. Now, this represents the angular size. I'm going to use a Greek letter. Don't freak out now. The Greek letter theta represents angular size, and it's just a little circle, like a zero with a line through it, okay? So this represents the angular size in degrees, okay? Now, we're going to use another letter, S. S is going to represent the physical size, or another way to think about it is the diameter. S is either the size or the diameter, and we're going to measure that in kilometers. And what relates the angular size to the physical size is, of course, how far away the object is. Remember that I attempted to demonstrate that by moving Moonball closer and further away from your camera. The smaller angular size happens when it's farther away. And so that third quantity is the distance. In astronomy, we tend to use little d for the distance. It's just kind of convention. So we've got three quantities here: the distance, the angular size, and S. They are all related to each other by the small angle formula. The small angle formula looks like this. The physical size is the angular size times the distance times 2 times pi divided by 360 degrees. Put a box around this. This is the small angle formula. And unfortunately, you've got to kind of learn the small angle formula to understand how to think properly about astronomy. This is your beginning exposure to it. So we're going to do a very simple problem, number 57. By the way, you guys know what pi is, correct? What's pi?
3.14.
3.14159265354. And what does that represent? The Greeks discovered it's the ratio of the circumference of a circle to a diameter. Anytime circles are involved, pi shows up, okay? Now, I want to demonstrate something with your Casio calculators about pi. Let me get, oh, I forgot to queue up the Logitech. Let me get out my Logitech control panel so that I can focus properly. Sorry, it takes a minute to load. Okay. Let me see if I can find the right focus for this. Something like that. Okay. Okay. On your calculator, there are buttons, and then there are little buttons above it in orange. For most of the buttons in orange, you have to hit Shift. Like, for instance, if you wanted to take the square root of 9, you'd hit Shift and then this button to take the square root of 9. One button is different. Your EXP key is used, of course, for scientific notation, but the EXP key is also the pi. But do you guys see how pi is in gray, not orange? That means something very special. Now, if you hit Shift and then you hit EXP, pi shows up. But here's what's crazy. You don't have to hit Shift. If you just hit EXP by itself, pi shows up as well. And that makes EXP a kind of dangerous key. You can use it for scientific notation. For instance, 2exp3 is 2 times 10 to the 3. That's, of course, 2,000. But if you do 2 times exp, then it's 2 times pi, which is 6.28. Be careful with that. Okay. Nina, could you please read us chapter 2, number 57?
Yes. Chapter 257. Sun diameter. Use the sun's approximate distance of 150 million kilometers and angular diameter of about 0.5 degrees.
Pause for a sec. How do we write 150 million kilometers?
1.5 times 10 to the 6th.
And that would be incorrect.
Oh, I'm sorry.
1.5 times 10 to the 6th is 1.5 million. This is 150 million, Nina.
Okay.
Try again. What does million represent?
What do you mean, what does million represent?
How many zeros?
Oh, 6.
So I don't
No.
understand why you were trying to put a decimal point between the 1 and the 5. I mean, I do understand, but I don't think you needed to do that.
Okay.
So it's 150 million. So 150.
150 times 10 to the 6th.
Good. All right. So they told us to use 150 million kilometers. Keep reading again.
Sorry, I lost it. Oh, and an angular diameter of about 0.5 degrees to calculate the sun's physical diameter. Compare your answer to the actual value of 1,390,000 kilometers.
Okay. We have 2 jobs. The first is to find the sun diameter. The second is to compare to the book value of 1. What did you say? 1.39?
Sorry, I keep losing it. Yeah, 1.39
million kilometers, right? I don't know if they put it in scientific notation or they wrote it out, but that's what it is.
Yeah.
Okay. We're going to use this formula to do that. This is just going to be very straightforward. We're going to put this in for the angle, this in for the distance, and we're going to punch and crunch. Let's write it out first. S, the diameter of the sun, is the angular size, 0.5 degrees. Make sure you put your units in there, just like me, times the distance, 150 million kilometers, times 2 times pi divided by 360 degrees. All right. Since some of y'all are new to the maths game, why don't we punch together, okay? We're going to punch all of this in one clean shot. Follow along with me, okay? So I'm going to do, I'd like you to see, I don't see there's any good way. I'm going to block this. There's nothing I can do about it. Let me get the focus tool here. Oh, man, it's a really tight window there. Looks like 49 or 50 is perfect. Okay, 50. So watch. We're going to do 0.5. There's the angular size. Times 150. We're going to use EXP6 times 2 times pi divide by 360 and then equals. Is this what you have? Show me your calculator. Show me. Nice. I like it. All right. Now that you have the correct answer, the question is, how do I format my answer? Because obviously I don't want all that crap. Is the number greater than 1 million or less than 1 million? Talk to me, people. I think we should bring that last problem back.
It's greater than 1 million.
So we have to put it in scientific notation. So tell me how to write this down.
It would be, sorry.
How many sig figs do you want to keep?
Just one.
Yeah, you're kind of right, but do you see how we're supposed to compare it to the book's value with 3 sig figs?
Uh-huh.
Let's keep 3 so that we can compare it to the books.
So 1.30, or are we rounding up?
You're always rounding.
Okay, so 1.31.
Right, because if you're going to chop an 8, the 8 rounds that to 1. So it's 1.31. What else?
1.31 times 10 to the 6th
Aren't you forgetting something?
kilometers.
That's right. Degrees cancel out here. The degrees here and here cancel out. And that's kilometers. Put a box around that because that's a classy move. And that's one of our answers. The last thing that we have to do is compare to the book's value. Now, comparing is something that you know, I mean something particular. Hello, Jeff. Welcome.
Hello,
to our
Professor.
class. You are showing up at the end of our homework session. That's okay. This has been recorded or shall be recorded. But what I'm going to need you to do, Jeff, is after today's lecture and after today's lab, you're going to be obliged to go back and watch this again so that you can get all the right answers down and submit that to me.
Okay.
Does that make sense?
Yes, Professor, it does. On Mondays and Wednesdays, I have about an hour lunch during the day from work. So I'm going to try to pick up an hour of lecture at least each day, just so I can stay involved.
Yeah, that's cool. I get that. And you can kind of hang out and participate for an hour. That's perfect. The way things are about to work here is we're just kind of watch what we're doing. I'm just about to end the homework. These guys have been working for a couple of hours. So I'm going to give them a little 10 or 15 minute break before I start lecture. Just because after 2 hours, you start to get the zap, you know. I could also use a cup of tea myself. And then a little after 12, we'll start our lecture proper. You can hang out for as much of this as possible. Did you get to watch the video from Monday by any chance?
I did. I watched about 80% of it, and I read the chapters in the book. And,
Did you do the lab? That's the key thing.
I didn't finish the lab. I plan on finishing that when I get out of work today.
All right, you have until Sunday at 11 p.m.
Okay,
get me
Sunday
that
at
lab.
11.
And
Alright.
so we did lab 1 on Monday. By the way, I meant to ask you guys, Nina and Whitney, how was that? You had to go get your calculators and then you went back and watched the video. Was it okay? Did you get it done?
Yeah.
All right.
Yeah, it got done.
All right. I felt a little bad, but it kind of didn't make sense without the calculator, right? And you guys submitted your labs?
Yeah.
Wait, Whitney, you're not done. Okay, look, we're getting sidetracked here. Look, there's one more step to do for your
Sorry.
your 25th point. I take
Oh.
this thing seriously. They want you to get the diameter of the sun, and we just calculated the diameter of the sun, but we're supposed to compare it to the book's value. And compare means something very particular to me, and therefore it needs to mean something particular to you. Obviously, the book's value is a little bigger. That's not what we want to say. We want to take a ratio. So I'm going to erase here for a second. I'm going to erase a little bit. You got this? My last lesson of the day is like this. From now on, in this class, when they say compare, compare to us means take the ratio. Now, there's an art to taking ratios. Sometimes you want to do the big guy over the little guy. Sometimes you want to do the little guy over the big guy. When they're close to each other, like they are now, I like to do the little guy divided by the big guy. So we're going to divide the size of the sun in the book by the size of the sun that we calculated with the small angle formula. Wait a minute, I'm sorry. Our value is smaller, correct? I already forgot. Was our value smaller than the books or bigger than the books?
Smaller.
Sorry, let me try that again. We're going to divide the size of the sun that we calculated by the size of the sun in the book. That is, we are going to divide 1.31 million kilometers by 1.39 million kilometers. Why don't you guys go ahead and do that and tell me what you get? Hey, Jeff, did you get this puppy?
I did, yes.
Awesome. What you get?
I got it's a big number. 0.94.
Okay, good. Stop there. That's good. What does 0.94 mean? How am I supposed to explain this?
Fraction?
Okay, a fraction. That's one way to look at it. But I mean, do you mean like a whole integer fraction, or do you mean? I like to think of it as a percentage. Anytime I have a number between 0 and 1, I think of it as a percentage, right? Does this have any units?
Kilometer?
Kilometers?
No.
No, because kilometers on top cancel kilometers on bottom.
Yeah.
There are no units. What does it mean then?
0.9% or 0.94.
0.94 is the decimal. What is it as a percentage? That's actually what I'm trying to ask you.
Oh.
What is that as a percentage?
94%.
That's right. That's what I want to hear. Our value, oops. Is 94% of the book's value. In other words, we got really close. And that takes care of homework number 1. Because I am a generous God, and because a lot of these problems I didn't quite get to during the first lecture, I have removed number 59 from consideration. So this special homework only involved 4 questions, okay? However, Nina and Whitney are now done, and they can take a photograph and upload that. Jeff and Nicole, you guys missed that session. So you're going to have to go back and watch this again and submit it to me before Sunday at 11 p.m.
Oh boy. Okay. I just went through the book and try to figure it out myself, and I
No, no,
already
no, no,
submitted
no,
that
no,
homework
no, no, no,
assignment,
no.
yeah.
I told Whitney this earlier. You are not allowed to think. You are not allowed to be creative. All you are allowed to do is copy exactly what I do and resubmit that to me. You
Okay.
are a baby bird, and I am the mama bird, and I'm giving you digested worms. That's all you're allowed to eat,
All right,
okay?
feed me.
Don't, yes, exactly. And that's going to be good for you, Jeff. All you need to do is put the time in to watch the video, copy everything down and submit it. That's all I want you to do. If
Okay.
you want to think about it along the way, that's between you and your God. All right. But I don't want you doing those problems on your own. I don't want you doing the labs on your own. I'm going to do it all with you. Okay.
Okay. All right.
You just need to make the time to watch those videos, which is significant, and get that down. That's what your issue is, an issue of time. So make sure you go back and watch that clip for lab 1. I
Yep.
gave you the timestamp where it is. Nicole, oh, you got your NASA shirt on. Do you know what that logo is called, by the way, Nicole? That's called the worm. Now, if you're a graphic design enthusiast and a NASA enthusiast, there are two different epochs of the NASA logo. There was the meatball and there was the worm. So NASA meatball versus worm. Now, I'm a worm guy, okay? Originally, the original logo for NASA was the meatball, which you can see over here on the right. And then in the 70s, they got all kinds of they wanted to revamp their logo and they made it what's called the worm. And now they've gone back to the meatball. But I got to say, if it's meatball versus worm, I'm all about the worm, okay? So just a little graphic design lore for you there. Anyways, Nicole, did you get lab 1 done?
I did, and I already submitted it.
You are awesome. Wonderful. Okay. So you missed homework 1 today. That's okay. Just go back after I post the video and watch that and do whatever I do. Now we're going to take a little break. It's currently on, oh my gosh, it's 12:07. I'm going to start. I want to be a little careful about this. We're going to take a longer break later, excuse me. I'm going to do a timer and I'm going to set it for 10 minutes. Okay. We're going to take a 10-minute break. Whitney and Nina have been going for 2 hours. They need a little pause. I could use a drink too. I mean, a non-alcoholic one, shall we say. Anyways, after that, we'll come back and we'll start today's lecture. Okay, can you guys do that for me? I'll see you in
Professor,
10.
I just have a quick question before you go. I'm sorry.
Yep.
So the old lab video that you posted, that's for the first homework. With
The first lab. So let's use the right terms here. The first lab. So you can see here under the announcements, Jeff, that because we did a pre-recorded lab because no one had their calculator, you go to this video and you scroll to timestamp 138 and you watch from there. This whole thing is really long. Just scroll to 1 hour and 38 minutes and that's where you start.
Okay, and as far as the homework assignment 1, that's the video that you just did currently. It's not the one that's posted there?
No, we didn't have a homework on the first day. We had a lecture here.
Gotcha.
And then I farmed out the lab. When I post the video from today here, it will have homework 1, lecture 2, and lab 2.
Fantastic.
So by the end of today, you'll be responsible for 3 items: lab 1, homework 1, and lab 2. All right. All right. Time's ticking. Let's take a little break. I'll see you in a few minutes.
Thank you.
Okay, folks, we're back and we're about to start lecture number 2. I've got a bits of scraps that I didn't quite get to in lecture 1. I'm kind of in a weird position here where I want to talk about seasons and I want to talk about angles. I want to make sure they're in your official notes. I already did talk about those things during today's homework. So if you have yet to watch it, you're going to get a snoutful there. And Nina and Whitney, they're going to get, they've already had that routine. But I want these to be in your official notes. So what I'm going to do is I'm going to cover those topics kind of quickly. I think it's very important that you guys kind of follow along with me and write down what I write down into your notebooks. So let's get some notes on those couple of subjects, and then we'll move forward to new stuff today. If I go too fast, you can ask me questions. Excuse me, and slow me down. All right. In last week's lecture, we had a subject called Earth's orbit. And I want to return to a few different issues there. The first one, and something I talked about during office hours today, is that there are 4 key points in Earth's orbit. And these 4 key points are geometrical alignments caused by the 23.5 degree axis tilt. So let's try to write that down. They are geometrical alignments with the 23.5 degree axis tilt. They are, in no particular order, the spring equinox. The spring equinox occurs roughly around March 21st each year. The summer solstice, which occurs roughly around June 21st. The fall equinox occurs around September 21st. And the winter solstice occurs around December 21st.
What is the difference between an equinox and a solstice?
It's about whether you consider it from an observational point of view. So let's start with equinox. And remember, these are geometrical alignments. So your question, Nina, is a good one. Let's pretend for a moment that you, the observer, are the sun, okay? So this ray of orange light coming from you, that's sunlight, all right? And I'm going to make a configuration here between the camera. Oh, that's weird. Sorry, I'm fiddling with my camera. I'm going to make an alignment between the camera and this Earth here. On the day of the equinox, the 23.5 degree axis tilt is at a 90 degree angle to the sun, and the sun is basically perfectly aligned with Earth's equator. The reason why it's called an equinox is because you're getting equal amounts of sunlight on the northern hemisphere and the southern hemisphere. Now, if you remember that picture that I showed you earlier with the different angles made between sun rays and the Earth, it does not mean that sunlight strikes all latitudes exactly the same. The sun is perpendicular to the equator, and as you get higher, the angle gets more shallow. So it's always a bit warmer on the equator than it is on the poles. What's important about equinoxes is that sunlight falls on the northern hemisphere and on the southern hemisphere in the same way. That is not true for the solstice. On a solstice, like for instance here would be the winter solstice, sunlight is more direct on the southern hemisphere of Earth and much more grazing and barely striking the northern hemisphere of Earth, okay? So solstices, I think the word solstice is related to the sun being at its highest point in the sky. You are going to learn a lot today about how the Earth rotates, how the sun moves through the sky, and timekeeping. It's actually wicked complex. This is going to be some of the most mind-bending stuff you learn all semester right now, right out of the starting gate. So hang on to your hats. You're going for a little ride. For now, if you look at my diagrams, Nina, let's go a few slides back here. You can see, for instance, in this picture, which I think is probably the best, You can see Earth going around the sun, maintaining its 23.5 degree axis tilt. And you can see that the equinoxes are occurring here when the sunlight shines equally on the northern and southern hemispheres. This is the winter solstice on the right. Notice that sunlight is more direct on the southern hemisphere, but although sunlight does hit the northern hemisphere, it's at a more grazing or glancing angle. That's why it's a bit colder. You're not heating up the ground rock as effectively. In the summer, the reverse is true. The northern hemisphere tilts towards the sun. The northern hemisphere gets more direct sunlight. The southern hemisphere gets more oblique light or glancing light, okay?
So equinoxes only happen in spring and fall, and solstices are summer and winter.
You've got it the other way. You've got it backwards.
Oh,
Summer and fall only happen at the equinoxes. You have cause and effect reversed. The cause of summer and fall and spring is because of the geometrical alignments made. Do you see my way of looking at it, Nina? See, I think the real thing is that the Earth is going around the sun. And our experience of summer and winter is caused by the angle that the sunlight is making with Earth.
okay.
You're thinking about it from the point of view of, I'm a human, and what's the first thing that affects me? And it's when I walk outside, is it hot or cold? I'm
Okay.
thinking about what's going on. And what's going on is the Earth is going around the sun, and that's causing that stuff to happen, right? Okay. So in any case, now I'm going to tell you something a little more complicated. There are not exactly 365 days a year. You probably already knew that. You know, the freaking Egyptians knew this. This thing goes back to like ancient Babylonian astronomy. People a long time ago, thousands of years ago, they figured out that there were not exactly 365 days in a year. Now, there are two different definitions for a year, and I'm going to need to explain both of them to you at some point today. But for now, let's just say that there's approximately 365 days and a quarter, which is how we get those leap years, right? Every 4 years, we add a day to keep our calendar in sync. You don't want springtime to start drifting around into August. Things will seem confusing. Because of this, the actual date of the spring equinox will drift by about 4 days each year until you have a leap year to reset it. The actual date of the spring equinox can vary from this marker sucks. It can vary from the 20th to the 21st to the 22nd to the 23rd. Even sometimes, I hate to tell you this, sometimes it even drifts into the 19th, but pretend I didn't say that because that's going to be even more confusing. It roughly varies by 1 of 4 days and then it resets again. What are we here? We're past the spring. We're heading towards summer solstice. So why don't we find out the exact date of summer solstice this year? I'm going to go over to Mr. Google here. I'm going to type summer solstice 2021. And you will see that Sunday, June 20th, the summer solstice will occur, okay? So that's now let's see what happens if we go to summer solstice 2022. Then it's going to be on the 21st. Guess what day it's going to be on the 23rd? Oh, it's still on the 21st. It hasn't drifted enough. Let's try 2024. Oh, wow. Well, shit's confusing. What can I say? Oh, it's changed. I'm sorry, it's changing it to winter solstice. I wasn't looking at what Google was doing there. Let's go back. Oop. Summer solstice 2022. Summer solstice 2023. Wow, it's still on the 21st. Now it's back to the 20th. It's a little, boy, that's even more confusing than I was expecting. How about 2029?
If you look at it though, it's changing each time. Like
Oh,
it
you-
went from 10 in the morning to 9:47 at night.
Okay. Now we're going to have to talk about that too. Basically, Nicole, what you're saying to me is what's up with the time? And that I can explain to you. The spring equinox is 4 things at once. And this is going to be a part of today's lecture. In fact, let's take this note next. It's going to be messy, okay? This is a note. Can I erase this? Do you have this, everyone? All right. Here's where we get into it. The spring equinox is 4 things at once. The spring equinox is a geometrical alignment between Earth's axis and the sun. That's what I think is the original thing. That's the most important thing. The second issue is it's also a day of the year. It's a calendar day. We say today is the spring equinox, right? And usually the spring equinox is roughly around March 21st, but you could see that when I was clicking through the years, it was wiggling around a bit. Okay, here's the next thing. The spring equinox is also a moment in time. You're gonna like that one less. I can see by Jeff's grimace there. Okay, Jeff, let me explain to you why it's a moment in time. Rather than do the spring equinox, which is a bit easier to demonstrate with the globe, let me try the summer solstice. As I tried explaining to students beforehand, the day of the summer solstice is the day where the 23.5 degree axis tilt points most directly towards the sun. A day before, it's not a perfect alignment with the North Pole. A day after, it's not a perfect alignment. The summer solstice is when the North Pole is tilted directly towards the sun. Otherwise, it kind of keeps moving in its merry way, and it's not perfect alignment. Okay, now slow your roll and think about it for a second, okay? During the day, the Earth doesn't freeze in its orbit and stop moving around the sun. During the course of a 24-hour day, the Earth is chugging along and chugging along and chugging along. And that means the real spring equinox. It's not really a day because during the day, the Earth will begin a little out of alignment with the North Pole. During the day, it will slide into the most perfectest alignment where the North Pole points towards the sun. That's you, you're the sun. And then at the end of the day, it will drift a little bit off. Do you see what I mean? So the real spring equinox, the perfect alignment, is a moment in time. Hence, Nicole was observing that when we were checking it out, the times were drifting. For instance, the summer solstice this year will not only be June 20th, but will be at exactly 11:31 p.m. And there's probably even seconds attached to that if you want to get real nuts, okay? Okay, here's the thing that you're going to like the least. The spring equinox is also a point on the sky. All right. Now look, I am going to be explaining that today, but you're not quite ready for that yet, okay? Let me say though, this issue can lead to hideous, evil questions that a mean astronomy professor could ask you on a midterm exam. I could ask you a question, describe the location of the spring equinox at noon on the spring equinox. Oh man, I hope he doesn't ask me that one. Okay, so anyways, the spring equinox can mean different things in different contexts, but guess what? It's all the same thing. It's just different ways of looking at it, okay? In my opinion, the first and primary issue is it's the geometrical alignment between the axis and the sun that is the cause of all these things. All right. As I mentioned during today's homework, one of the things that the alignments cause are seasons. And once again, I'm going to run through this quickly because I already did this for for Nina and Whitney. Either Jeff or Nicole, can you tell me what day of the year this is? Look at this picture. What day of the year is this? Nina and Whitney can't answer because they already know.
What day it is?
Yeah, you should be able to look at this configuration in this picture and tell me the day.
That would be the equinox,
Let's go back a slide. Okay.
December 21st.
Nicole got it. How did you know it was December 21st, Nicole?
Previous slide.
Say
It
that.
showed from the previous slide, it showed the winter solstice, but it said the dates were between the 21st, 24th.
Yeah, but here's the answer that I wanted you to give me, Nicole. The reason why you can tell that this is the winter solstice is because the axis tilt, the northern hemisphere is tilted away from the sun. The southern hemisphere is tilted up towards the sun. That's what tells me this is the winter solstice, okay? All right. Now, in an argument that I made earlier, but I have no trouble repeating myself, imagine that you've got two beams, two flashlights, equal flashlights, and each flashlight contains an identical beam of energy. As you know, sunlight equals energy. If you stand outside with your black shirt on, you start to feel warm and you know it's the sunlight doing that. So in the most basic way, you know that the sunlight contains energy. These two flashlights are equal. They contain equal beams of energy. The difference is the angle. This flashlight shines on the ground in a perpendicular angle. The sunlight's concentrated here. This flashlight strikes the ground at an oblique angle, and the sunlight is concentrated here. Which patch of ground rock is going to be warmer? The rock on the right or the rock, sorry, whoa, I don't know my left from my right. The rock on the left or the rock on the right? Which patch is going to be warmer?
The left,
How do you know the left is going to be warmer?
just by the position of the angle, it's getting direct sunlight or direct light from the flashlight versus.
Okay, so how does direct light, yeah, Jeff?
I would say the right one because there's more cover, there's more surface area. It's more energy's hitting a wider area.
Let's talk about that area. I agree with you, Jeff, that this is more area. I do not agree that it's more energy. The diameters of the beams, the energy contained in the beams is the same. That means in the right case, you're spreading out the same amount of energy over a larger amount of area. On the left, you're taking the same amount of energy and you are concentrating it in a smaller area. The left rock will be the warmer rock because it's equal energy but less area. You're not here, you're spreading the jam out too much, okay? Now, go back to your winter solstice. And, you know, Whitney and Nina are going to have to forgive me, but you guys probably should hear this too. If I labeled all of these beams 1, 2, 3, 4, 5, 6, which beam is most effectively heating up the ground rock on Earth? Which beam, 1, 2, 3, 4, 5, 6, is doing the most effective job at heating up the ground rock on Earth?
1.
3 or 4.
It's got to be one, only one.
So 3.
3. Why is 3 the most effective at heating up the ground rock, Nicole?
Because it's focusing on a smaller area.
Because the rays are perpendicular to Earth. But what you said is also true. The rays will be most concentrated here because the beam will be most perpendicular. Therefore, if you wanted to go to the hottest place on Earth on December 21st, where would you go?
23.
Right, but you would go to 23.5 degrees south latitude, the Tropic of Capricorn. And so you would go to Paraguay or Sao Paulo in Brazil. You go to Sao Paulo. If you want to be at the hottest place on Earth, there's a little more to it. December 21st will not end up actually being the hottest day in Sao Paulo because Earth experiences something called thermal lag. If you guys think about it, if you're in Rhode Island, what should be the hottest day of the year in Rhode Island? What should be the warmest day of the year in Rhode Island?
June solstice.
That's right, the summer solstice, June 21st. But now think about your own personal experience as a human in Rhode Island. What is the actual hottest month?
July,
Maybe even August.
August.
Jeff, why is August or July the hottest month when the sunlight is most concentrated on us in June?
Because that's not the exact point of time that it's going to be.
It's for the same reason why if you put a warm beer into a fridge, it will take time for it to become a cold beer. Just because you put the beer into the fridge doesn't mean it's immediately cold. There's thermal lag. It takes time for a thing to cool down. It also takes time for a thing to heat up. So the most concentrated rays, they're doing their most effective work in June, but after a while, the ground rock, after a month or two, starts to get really hot. You're going to have to learn about how the Earth gets hot. It's actually more from radiation from the ground than above, but we'll get to that at some other date. Anyways, I can't give it to you all at once. You have to take it in little bite-sized pieces. Let's talk about what we just learned. We need some notes here, okay? Let me explain what you just learned. First of all, when we talk about planetary seasons, seasons are different depending on where you go on Earth. In New England, we have a perfect equipartition, 4 seasons per year: spring, summer, fall, winter. In places like Ecuador on the equator, they only get 2 seasons a year. The equinoxes are like the hottest days of the year. That's summer for them. And they don't even have a real winter. When the sun drifts a little bit off of the equator by 23.5 degrees, those are the monsoon seasons. So even where you go on Earth will change seasons. But from our point of view, we're talking about planetary science in this class. We have to have a big picture perspective. Seasons for us are a change in global temperatures over one planetary orbit. In Earth's case, it's a change in temperatures over the course of a year. But I got to tell you, there are other planets out there. They have seasons too, and it ain't over 1 year, okay? All right, now that we know that, what is the cause of seasons? Well, 1, axis tilt. 2, for some planets, it can also be a change in distance from the sun. But here's the kicker. Most planets have really close to circular orbits. So if you want to keep it stupid and simple, here's how it works. Axis tilt is the cause of seasons for most planets. And usually, more tilt equals more seasons. And that's at least up to 90 degrees.
Can I ask something?
Sure enough.
I thought maybe I misheard you, but I thought earlier in our like office hours, you said that the change in distance from the sun wasn't a cause of the season. It was like primarily axis tilt.
I'm going to tell you something, Nina, right now. I lied to you. And it won't be the
Okay.
last time I do that, okay?
Okay.
You weren't ready for the truth then. You were ready for the lie. And so that's what I spoon-fed you. And now I dared to reveal one more onion layer below, okay? And I told you that sometimes it can be changed. But here's because I included why I lied to you. Most planets have wicked circular orbits, Earth included. So for the most part, the tilt matters way more than the distance. I lied to you when I said the distance doesn't matter because I thought it was funny to do so. Now let's take a look at let's look at the orbital inclinations of the planets for fun. So axis tilts of planets. Let's see if we can get a little a diagram here would be kind of nice. Okay. This might work. Why don't we peek around the solar system? All right, that's not high resolution enough for me. Here we go. Ooh, that looks good. The obliquity. Now, if you want to really get your $500 worth, let's learn a fucking fancy vocab term there. The obliquity of the 9 planets. The axis tilt is known as the obliquity. An oblique angle is a glancing angle. I want this picture more than I've ever wanted. Oh yeah, 9,000 pixels. Give it to me, baby. I dare you. Okay. Now, tell me, students, which planets would you expect to not have seasons? Take a look at the picture here and tell me
Mercury.
pardon?
Mercury?
Mercury does not have seasons, correct. What else?
Jupiter.
Jupiter does not have seasons. Who else?
Yes.
Weirdly, Venus is so tilted that it's almost at 180 degrees. These
Wow.
planets do not have seasons. The rest of the planets do have seasons. Earth and Mars have almost the same axis tilt. Earth and Mars almost have the same seasons, except they don't, because Mars is one of those planets where it actually has a significant distance variation, so that starts to add to it. One of the most extreme seasonal variations in our solar system would be the planet Uranus, which is basically flopped over on its side. As I told you before, for 30-something years, for 34, 35 years, only one hemisphere of Uranus gets sunlight while the rest is shrouded in darkness. For the next 34 years, only the north hemisphere gets sunlight. Basically, a day on Uranus is like 60-something years. Okay. The days and the nights are not always have the same relationship on different planets.
For Venus, so the tilt on Venus is so extreme that like it doesn't have seasons, basically.
That's
Yeah.
right. In fact, there's another sleight of hand going on there. You might ask the question in a different way. If Venus is flopped upside down, why even define it? Why not call this the North Pole? Okay. Every planet in our solar system spins counterclockwise with one exception, Venus. Venus is so screwed up that it actually has a retrograde spin, and it has a clockwise spin as seen from north. For some reason that probably has to do with computer modeling or something, astronomers have chosen to then define north on Venus as upside down. I don't know. It's a matter of semantics, but Venus actually spins backwards. That's why they say its axis tilt is 188 degrees. Another way to look at it, yeah.
Was Venus spinning retrograde when it got captured by the sun's orbit and it came in that way? Or why is it spinning different than the other?
That's a question we are going to answer, but you're not ready for it yet, Jeff.
Okay.
In the future, when I can USB all this information directly to your brain, there are too many puzzle pieces left to go there. The quick and dirty answer is Venus formed with the solar system along with the nebular hypothesis. But the answer to your question is it probably did at one point spin faster and then some big bastard struck it and forced it. It's probably collisions. The early solar system was a very violent place, as you will discover. But we're going to come back to that later, Jeff. It's a cool question. It's just, you're going to get me all excited. I'm going to start.
Yeah, I'm
foaming.
sorry.
Okay. No, it's all right. It's okay. We got to do this. That's what's fun about the live class. Okay. So this is why we want to do some live stuff. All right. We covered the season thing. Let's deal with the angle thing next. And then we got some big vocab stuff to do. All right. So now we have to talk about angular size, which played a huge role in today's office hours. It would have been nice if you guys had this lecture first. Sometimes things happen upside down, right? So angular size. We're going to have a symbol for angular size in this class. It is a Greek letter called theta. Don't freak out too much about theta. It's just a 0 with a line through it. Because the Greeks loved geometry, we oftentimes use Greek letters for angles so that the reader kind of knows, oh, that's an angle. It's kind of a cute little thing that we do. Here's the idea. You see angles, not sizes. Okay? As a demonstration of this, consider an experience I'm sure all of you have had at some point in your lives where you go out at night and you're looking up at the sky, and maybe it's around Halloween or something, and you see the moon rising, and you see this big, evil orange moon coming up over the horizon, and you look out the window and you say, holy cow, the moon is huge. The next time you see one of those huge moons, I challenge you to take your finger outstretched when you see the big, scary orange moon and hold your finger at arm's length up against the moon, and you will discover the moon, even when it's huge, only covers roughly half the width of your index finger. All right? Now, wait a little while. Go do something. And as the moon rises higher and higher in the sky, it won't look huge and it won't look orange anymore. It'll look like the good old-fashioned white moon that you know and love in the sky. And when you see the moon higher in the sky and it doesn't look huge anymore, I want you to take that same finger back out and hold it up against the moon at arm's length, and you will discover it's exactly the same width. It's still exactly half of your finger, and the size hasn't changed at all. What has changed is your brain's interpretation of the angle. You have been victim of something known as the moon illusion. Your brain psychologically relies on visual cues to understand how big something is. Basically, you do math without realizing that you do math. When you see the moon against a foreground of cactuses and buildings and rocks and trees, when you see it coming up over the horizon and you have some depth perception, your brain is hardwired to say, holy shit, that thing is behind all of that stuff. It's behind all the buildings and the trees and the mountains, and it's half of my finger. That thing has got to be insanely huge. The problem is once the moon gets up there on the sky, you kind of lose all depth perception. If you think about the moon, it doesn't look particularly big, but it also doesn't look particularly small. You can just kind of see it and it hangs there. It's really difficult for your brain to understand how big the moon is when there's nothing in the foreground to judge it against. In any case, this isn't just true about astronomical objects. It's true about stuff in your everyday life. This marker subtends some angle in your field of view. This Sax's Frisbee subtends an angle in your field of view. And your camera functions just like an eyeball. If I bring this disc closer and closer to the camera, it covers a bigger angle and it eclipses your field of view. And as it gets farther and farther away from you, its angular size becomes smaller. Okay, so what are we going to do about that? Well, we're going to need to think about how we measure these angles. And as I just mentioned to you, astronomers sometimes use their hands as a crude angular measurement tool. If you want to talk about degrees, which are the most basic unit of angle, a degree, as you learned today, is 1/360th of a circle. Your outstretched finger is about 1 degree. Your outstretched fist is about 10 degrees. And if you do that Hawaii hang 10 thing, pinky to thumb outstretched, that's about 25 degrees. And astronomers will often hold up their hands against the sky to crudely measure things. On the other hand, my little mouse pad here is a more sophisticated tool for measuring angles. I could use something like a sextant, and I could take quite precise, it's basically, you know, a protractor with a little telescope, and I could use this to take very precise angular measurements of the sky. Today, I'm going to have a lesson on celestial navigation, if I can ever get there. So maybe y'all get to learn a little bit about that. Unfortunately, degrees are a sucky unit to use in astronomy. Let's take a look at why. So our first unit, we're going to have 3 units for angular size. The first is the degree. And 1 degree is defined as a 360th of a circle. That's one way to say it. Another way to say it is, in 1 circle, there are contained 360 degrees. And that's actually a type of conversion factor. Here's an example. The angular size of the moon is approximately ½ a degree. And by a weird coincidence of nature, the angular size of the sun is also ½ a degree. Now ask yourself, what the shit is up with that? Is the sun the same size as the moon? What's bigger? I think you know the answer to this, but I want to be.
Sun.
The sun's bigger. Which one is farther away from Earth?
Sun.
So that's pretty messed up, right? Because what that says is, through randomness, through total freaking randomness, and let's look at a picture so we can understand this here. It must be that the sun is farther from Earth by the exact same ratio that the sun is bigger than the moon. Like if the moon had formed a little bit bigger, 2 times bigger, if the moon had formed closer or farther away, if Earth had formed a little closer to the sun or farther from the sun, none of that would be true. But because it just so happens that the sun's diameter is 400 times bigger than the moon's, and it also just so happens by pure coinkydink that the sun is 400 times farther from the moon, they have the exact same angular size, and therefore we on Earth get treated occasionally to the grandeur that is a total solar eclipse, where the disk of the moon perfectly blocks the disk of the sun. As you were going to see in today's homework, and maybe you'll see in a future homework, occasionally this is not true. The moon's orbit is not perfectly circular. And from time to time, you can have eclipses where the moon is a little bit further away. And that's when you can get weirdnesses like an annular solar eclipse, where the angular size of the moon does not perfectly cover the disk of the sun. Those are very rare and beautiful types of eclipses to see. It also raises another question. The moon and the sun are the biggest astronomical objects on our sky. What do we got after the moon and the sun? We got planets, we got stars, we got galaxies. If these things are already ½ of a degree, then the angular sizes of planets are going to be so tiny for astronomers, we're going to have to measure them as 0.000 something degrees, and that's going to get irritating. For that reason, astronomers had to make smaller units for angle. You guys got this? All right, let's get the other 2 down now. Okay. The second unit that we're going to deal with is the arc minute. The symbol for an arc minute is one with an apostrophe. An arc minute is defined as a 60th of 1 degree. So in other words, you take a degree, as I mentioned before. Let's get back up there to this slide. You chop your 1 degree up into 60 slices, and each one of those little slices is 1 arc minute. The conversion factor that you want is 1 degree contains 60 arc minutes. As a basic example, the angular size of the planet Jupiter is approximately 1 minute of arc. All right. At this point, I think it might be useful to tell you something that's not in the book, but is kind of really important to astronomy. The human eye if you have good vision, like 20/20 vision, the human eye can see down to an angular size of something like 3 minutes of arc. And that's good vision on a clear day. And what's the difference between something that is above or below that threshold? It's about whether your object is resolved or unresolved. A resolved image will show you a disk. And the disk will be differentiable between top and bottom. This is an optics issue, okay? Here, an unresolved object can still give you light, but it will appear as a tiny point source or a speck of goo. A star would be an example of an unresolved image. We refer to this in optics as a point source. It might be a source of light, but you really can't see anything about it. You can't distinguish any features. Perhaps I could give you guys an example of this in dramatic photographic form. One of my buddies, Bob Horton, was the president of the Skyscrapers, the Amateur Astronomical Society, and he knows a lot about telescopes and astrophotography. He took a couple of beautiful photographs that I asked him for so I could share with you guys, because they're kind of a cool demonstration of what's going on. Here you can see the city of Providence. I'm guessing he was probably either at Prospect Park or maybe on the roof of the Barris and Holly building at the Brown campus. Actually, I think that building on the right is the science library. So he's probably standing on the roof of Barris and Holly right near Thayer Street, and he's looking down towards downtown. That's where I am right now. Okay. Now, up in the sky here, you can see 3 of the brightest objects in the nighttime sky. And let me walk them up for you. This is the star Sirius. Sirius is actually the brightest star in the sky. Now, I know what you're thinking. You're thinking, that don't look too bright in the photograph. Well, fine. That's because he took this photograph for aesthetic purposes, and he exposed the camera in such a way where you can see the beautiful lights of our fair city. Compared to the lights of our city, Sirius is dim, but Sirius is the brightest star in the sky, and if you were standing there on the roof of the building with him, that would probably look pretty dramatic. We can also see 2 planets. This planet is the planet Jupiter. This planet is the planet Venus. I want you guys to notice a couple of things. The brightnesses of the planets are much greater than the brightnesses of stars. Planets are brighter on the sky than stars are. Notice that Venus is actually brighter than Jupiter. That's because it's a bit closer to us. Are these planets resolved or unresolved images in this picture?
Unresolved.
They're unresolved. Is the Superman building, the Industrial Hospital Trust building, is that resolved or unresolved in this picture?
Resolved.
It's resolved because you can see the top of it distinct from the bottom. Okay. Now, in the next photograph, Bob took basically what is a little telescope, a telephoto lens, and attached it to his camera. And I want you to watch what he sees. So he's going to zoom in using a telephoto lens. And now here's a zoom in of Jupiter and Venus.
Wow.
Cool, right? Okay, now let's take a look at what's happening. Now, not only can you see Jupiter, right? But you can also see the 1, 2, 3, 4 Galilean moons spread out next to it. You can also see Venus, and notice that Venus is legendary for being the only planet besides the moon that goes through a full set of phases. You can actually see Venus go through a full set of phases like the moon. Okay, questions for my students. In this photograph, is Venus a resolved or a unresolved image?
Resolved.
Resolved because you could actually see the phase, the gibbous phase of the planet. Is Jupiter a resolved or unresolved image?
Unresolved.
It's resolved. And the reason why it's resolved is because you can see it as a disk. And that is the real disk of Jupiter. That's the top and that's the bottom. What about the moons? Resolved or unresolved?
Unresolved.
Very good. Those are point sources. Now, I just told you that the angular size of Jupiter is about 1 minute of arc. So the angle that you're seeing there is 1 arc minute. You can see that if we wish to study the moons of Jupiter, we're going to need even smaller units of angle. Sometimes even arc minutes are too clumsy for astronomers. That's why not only did we invent the arc minute, but we also invented the arc second. Okay. An arc second does the same thing to an arc minute. The abbreviation for arc second is a 1 with 2 apostrophes next to it. It is defined as a 60th of 1 arc minute. Probably the better conversion factor is in 1 arc minute, there are 60 arc seconds. So we have arc minutes, arc seconds, and degrees. Those are the different angles we'll be using over the course of the semester for angular size. Just for fun, what is an arc minute really? An arc minute is sort of like looking at a dime from 2.5 miles away. A dime 2.5 miles away subtends an angle of 1 arc second. Obviously, I don't know if it's FDR or LBJ on the dime, but you cannot make out that dude's face from 2.5 miles away on a dime. Your eye cannot resolve 1 arc second resolution. As an example of just how stupidly tiny the angular sizes of stars are, and that's slide 42, consider the great star Betelgeuse in the upper shoulder of Orion. The angular size of the star Betelgeuse is 0.055 arc seconds. That is 55 thousandths of an arc second, or 55 milli-arc seconds. The angular sizes of stars are in fact so microscopic that even the world's best telescopes cannot resolve the disk of stars outside of our solar system. To date, there is only one picture that we have a resolved image of the surface of the sun. One picture, one star that we can image the surface of, and that is the sun. Now we have some truly dramatic photos of the surface of the sun that I'm going to share with you eventually. But isn't it sad that none of these other stars, we can't actually see what they look like? Okay, there's one star. We kind of did it with Betelgeuse, but you're not going to like it. This is our best picture to date of the star Betelgeuse. We barely resolved it. Hold on, that's not real. And this is what our best picture of the star Betelgeuse looks like. Pretty shitty, as you can see. We can't even really, we can sort of, it's not even really anything but a blob, you know? On the other hand, the photosphere of the sun is highly resolved because it's quite close to us. And we can actually, let's find a real picture. Photosphere of the sun granules. We can actually resolve little blobs of plasma that are rising and sinking at the surface of the sun. They're called granules. I don't want to spoil all my tricks just yet. This is a picture of a sunspot. Look at, whoa. Well, we're going to get to all this stuff eventually. That just came out a couple of years ago. This is a high resolution of a sunspot on the surface. Look at that shit. That's like that's like something out of your nightmare. It looks like the eye of Sauron or something.
What was that taken with? Was that the Hubble?
No. Hubble doesn't do this. It was either taken with the Solar Dynamics Observatory or more details. What is this picture taken with? Let's see.
What is a sun?
Stay tuned.
Okay.
If you get me excited about it, then I'm gonna screw up this day. This was taken with the Swedish 1 meter solar telescope in Norway with some filters on it. Huh. I wonder if there's a picture of that out there. Cool. This guy took that picture.
Wow.
Nice. Okay, more on the sunspots later. You're gonna get to all that. All right, now we got to learn a formula. You already kind of used it in your homework. Every class, you got to learn a formula to understand how astronomers think. And this formula, you've already seen it. Let's draw the picture one more time for our notes. The rest of you will get it, more description of it during the office hours. The picture is that we have an astronomical object like a star or a planet. It's going to subtend some angular size. Where's, hold on, guys. I lost my meter stick here. Here it is. All right. You're looking at the star from Earth. Could be a star, could be a planet, could be whatever. It has an angular size theta. Usually we're going to measure those in units of degrees. S is the diameter of the star. Usually we'll measure that in kilometers. D is the distance between you and the star. Usually you want to measure that in kilometers. Distance, size, angle. They're related by the small angle formula. Sorry. The small angle formula says the physical size is the angular size times the distance times 2 pi over 360 degrees. Okay, although we did this in our office hours, I think we should do it again as an example. You guys have your calculus handy here? All right. Example. Find the diameter of the moon. Okay? I'll tell you that the angular size, you already know, is half a degree. I'll also tell you that the distance is 384,000 kilometers.
Just to clarify, that's 2 times pi on the top there.
Yeah,
No.
sometimes I use a dot. I was afraid you would think the times was an X. That's what I was worried about, Nina. All right, tell me how to do this, guys. Bust out your calculator. Nicole was dying to volunteer. She mentioned that to me earlier, that she wanted to be the first person I called on when we did a math problem. Isn't that right, Nicole?
Sure.
All right.
Just give me 1 second. I'm finishing writing it down.
Sure, take your time. Finish writing that down. I will sip some of my polar seltzer while you do that.
Okay.
So what do I do?
So, well, I like to do things more visually, so I would rewrite the problem first by like inputting all the numbers into where.
I fully agree with you, Nicole. I think that's exactly what we want to do. So here's our example. Find the diameter of the moon. We've got our angle and we've got our distance. S equals 0.5 degrees, right?
Mhm.
Times 384,000 kilometers times 2 times pi divided by 360. Remember, if you missed our office hours today, you can activate pi on your calculators by simply hitting the EXP key. But be careful with that EXP key. It's not only your scientific notation key, it's also pi. It depends how you hit it. All right, why don't you guys, look, you're going to learn something either way. Try to plug it in without my help first. Show me what you get, and then we'll learn how to do it right. But take a moment to see if you can do this on your own. I want to see who can get it and who can't. Punch it all in one shot.
How do you do pi again? I'm sorry.
You simply do, well, EXP is the pi key, but if you want to do 2 times pi, you do 2 times pi, okay? If you do 2 pi, that turns it into the EXP key, and that gives you scientific notation. Be careful with that. I just want to see if someone can get me an answer. Did we lose, did we lose folk? Oh, Whitney's still around. Okay. Whitney's in troll mode. That's fine. You put some time in so far today. That's okay. I just don't want to be talking to an empty bunch of boxes. At that point, I'm like, fuck it. You just watch the video. Okay. Because what's the difference, right? If you all want to troll, that's the same as watching the video. Why make me a prisoner of nothing? What'd you get? Show me your calculators. Hold them up. I want to see what you got here. You got it, Nicole. You got it, Nina. Jeff, talk to me, baby. Do you have your
I'm on
calc?
my calculator. I'm at work, Professor.
All right. From now on, your calculator goes where you go. All right.
You got it.
You
You
take
got it.
that with you. Okay. Well,
Will
if
do.
you're going to be, it's good to practice this stuff, you know, because later on you'll forget to do it, you know. So have that with. I'll tell you what, they're only $8. Buy a work calculator, buy a home calculator. You have one for, you know, just double your
Fair
money.
enough.
Okay. All right. How should I round this, Nicole? What do you want to round that to?
Oh, sorry, I didn't realize I was muted.
What are we going to round that to?
Should we move the decimal place
No,
first?
I'm not
No,
talking. Is this number greater than 1 million?
no.
Then we do not have to use scientific notation.
Okay.
But just because we're not using scientific notation doesn't mean we're not obliged to round this into something tasteful and honest.
Okay.
The answer is
Then-
not 3351.032164. That's not how we roll. All
Yeah.
right.
Then I would round it to 3,350.
Be even bolder. That's not bad, but I say be even a little bit bolder.
Just 4,000 maybe?
Well, it's clearly not 4,000 because it's 3,300 or
Okay.
3,350 does not round to 4,000. So that just doesn't make any sense.
Okay.
Because if you're going to round to one significant figure, the second digit's a 3. So you cannot increment the 3 to a 4, right?
Yeah.
However, if you kept two significant figures, then what would it be?
34,000.
3,400 or
Yeah, sorry.
3,000, right? All right. So your answer is 3,400. What are the units? Nicole, I need some units.
Kilometer?
That's right. Degrees on top and degrees on bottom cancel. That makes sense too, because the diameter of the moon should be measured in kilometers. The moon is 3,400 kilometers across, all right? That makes it roughly a third the size of Earth. Well, actually a fourth the size of Earth. 12,000 versus 3,000.
We should always round our answers.
Yeah, absolutely. Absolutely. That's just good taste. That's decorum. It's also honesty, Nina. You only have 3 sig figs there and 1 sig fig there. You've barely got 2 as it is. More than that would be fibbing. The true diameter of the moon, by the way, is 3,476 kilometers. So 3,350 wouldn't have been accurate or precise. Okay, now you learned about the small angle formula. Module complete, okay? That's coming back to, oh, let's throw one more piece of business in there. Sometimes you don't want to just calculate the diameter. Sometimes, including on the exam, I'm going to make you calculate the angular sizes of things. In that case, you can do a little algebra and rearrange this formula to solve for angular size. Erasing this. So if I wanted to give you the quick and dirty version, the small angle formula, but this one is solved for angular size. The angular size of an astronomical object can be computed by doing 360 degrees divided by 2 pi times the diameter divided by the distance. The diameter and the distance need to have the same units. That was the final homework problem that we were going to do today. In the interest of time, and because I didn't move fast enough, I cut that homework problem. But you are still responsible for that technique. So at some point, we should probably work out a sample problem with that, but not now. All right, so now you know about the fact that we see things in terms of angles. Now it's time to get real. Now that you know it's all about the angles, now you can learn how to describe the motions and the trajectory of stars as they rise and set across your sky. That's the rest of our business today. How do we track stars as they move across the sky? How do we measure their positions and their coordinates? All that good stuff. We're going to take a little tea break at 1:30 because I know you guys need a break. It's 1:23. Let me see if I can squeeze off one more module, but I'm going to set my alarm because I sometimes talk through tea break. So I'm going to set an alarm for 1:30. Oh, I already got one. Cool. All right. Let's see if I can squeeze out a little tiny piece of business before we do that. It's time to learn about a concept that you're going to be doing in lab today. This little bad boy here is a concept that was invented by Greek astronomers. It's called the celestial sphere. It's not real. It's a lie. Now, the Greeks, they actually thought that the stars were stuck to a crystalline sphere that rotated around Earth. Those silly Greeks. That's not true. But you know what? For all intents and purposes, if you're an observer on Earth, it's kind of like the truth. It's actually a useful lie, because when you're watching the stars rise and set, they are basically rotating on a big spherical dome we call the sky. And that spherical dome is called the celestial sphere, and it's kind of a big deal in astronomy. Introducing the celestial sphere. The celestial sphere is a useful lie, okay? And it's defined in the following way. A sphere of infinite radius on which stars, planets, moons, galaxies, anything else that goes bump in the night seem to rotate. Hey, Jordan, could you activate the air conditioner at like 72? I'm starting to get the hot flashes here. A sphere of infinite radius on which stars, planets, moons, galaxies seem to rotate, okay? I have a nice little slide for that. Well, sort of nice slide. Let's see here. Put you guys over there. Let's start you off with this one. Okay. Here I've oriented the celestial sphere so that north appears up. That's kind of nice. There are 3 key points that we'd like to define. If you project Earth's north pole up onto the sky, that's actually a point on the sky called the North Celestial Pole, all right? You can also project the South Pole onto the sky, that's the South Celestial Pole. You can also project the Earth's equator onto the sky, and that's the celestial equator here. Now, in this diagram, they seem easy and obvious because I've oriented the celestial sphere so that north is up. But when you're standing at a random spot on Earth, like Providence, Rhode Island, these things are not so easy or obvious to understand. For instance, a slide or 2 back, here I've tilted the Earth by 23.5 degrees. Now you can see the North Celestial Pole is here, the South Celestial Pole is there, and the celestial equator is the red ring that you see here. Those are the first 3 sort of points that you've got to identify on the celestial sphere. 3 points. So we have the North Celestial Pole. By the way, I'm going to start labeling this because we're going to use it a lot. NCP, okay? Little abbreviation there. The North Celestial Pole is the projection of the North Pole onto the sky. We have the celestial equator, the CE, and that's the projection of the equator onto the sky. And then we have the South Celestial Pole, SCP, and that's pretty obvious. It's the projection of the South Pole onto the sky. Cat's got all that? Sorry. Jeff, at some point, me and my friends, when we did the college thing, we had this debate. Is it better to take the notes or is it better to listen and think? Because we definitely found that if we were taking the notes, we weren't really thinking about it. If we weren't taking the notes, we were thinking about it, but then we didn't end up with notes. Now, it's up to you to decide how you want to do it. But I think writing a lot of this stuff down is useful only because it takes time. I don't think you're going to have enough time in life to go back and rewatch this again. It honestly might not matter because you can do all the homeworks with me and all the labs with me, and you can just put a blindfold on and click buttons through the midterm exam, and you could probably pass this course as long as you do everything. But I want to mention that writing some of this stuff down will be helpful at some point, especially the 4 steps of dimensional analysis. All right, that's tea break, but we're not quite there yet. I got one last point to make, or 2 last points to make. There is a special object located at the North Celestial Pole. Do you know what it is?
North Star.
That's right. What's the name of the North Star?
Syria? No.
Not Sirius.
Oh, I know it too.
Begins with a P.
Polaris?
Polaris. Very good. Let me tell you guys a little. Let's pretend like this was the astronomy class you thought it was going to be, where I'm like, here are the constellations, and this is what happens when the Hercules. Okay, no, we're not doing that. Anyways, but let's pretend for a second like it is. You guys know the Big Dipper, right? Okay. And the Big Dipper is part of a constellation called Ursa Major, the Big Bear. This is the tail of the bear, and this is the butt of the bear. And he's got some other stuff too. Now, if you can find the Big Dipper, the front 2 stars are called the pointer stars. Make a line in the sky with the pointer stars, and they terminate on Polaris. That's how you find Polaris. Now, it turns out that Polaris is part of a constellation Ursa Minor, the Little Bear, but we also call it the Little Dipper. However, let me tell you something. Unless you live in a really dark sky, unless you're down in like Charlestown or something, from Warwick, from the CCRI Observatory, I can see Polaris. It's not very bright, but I can see it. I can see this star, which is called Kochab. I forget what this guy's called, but I can see him too. These stars, there's too much light pollution. If you're out in the deserts of Texas, then you could probably see the Little Dipper would actually shine bright. But the Little Dipper is kind of hard to see. The Big Dipper, on the other hand, is easy to see. So if you want to find Polaris sometime, use the pointer stars, make a line, and they terminate on Polaris. Let me show you where we're going with this. During the course of the night, if you were to take a camera and put it on a tripod and point it towards Polaris, you would see stars rotate and orbit around Polaris. As Earth spins, Polaris kind of keeps a fixed position, and all the stars kind of seem to rotate around it. People make a cottage industry out of taking photographs of these star tracks or star trails. Some stars are so close to Polaris that we call them circumpolar stars. They never actually set below your horizon. I'll define that later. I want to make one other point about this. This is not an obvious fact, so I want to go back a few slides to explain it to you, and then I'll let you take the tea break. You can always see exactly 1/2 of the celestial sphere in your local sky. So after tea break, we're going to talk about the local sky. That's the dome of the sky that you see when you're outside at night. Let's talk about why that is. When you're standing over here, where this arrow is, you tend to think of yourself as like a little dude standing on a big Earth. And you imagine that yourself is surrounded by like a little dude sky centered on you. But I'm here to tell you that your sky is not a little dude sky, it's a big dude sky. And your sky is actually all of this. How can that be? All of this is your sky because the Earth is actually really, really tiny in comparison to the celestial sphere. In fact, to draw this better, you'd probably want to draw it, let's clear all drawings, a little something like this. The Earth is a tiny little dot. The celestial sphere is a huge ass circle. And if you're standing here on Earth, there is no difference between your feet and the center of Earth. So your horizon actually stretches like this. And all of this is your local sky. That's something that would not be obvious unless an astronomy person told it to you. So let's take that as a note, and then we'll take tea break. Your final note about the celestial sphere, throw it wherever you can, is this. You can always see exactly 1/2 of the celestial sphere on your local sky. All right, it's time for tea break. We kind of got a lot to do today. How do I want to do this? This is going to be a long day, and I'm feeling it just like you guys are. I'm going to give us a indulgent 25 minutes, but then we come back, okay? How does that sound? 25. I thought about 20 minutes, but I just want a little more, you know? How do you guys feel about that? The reason why, remember, for those of you just joining us, the reason why we do the tea break thing is we had 2 hours of homework, little break. The lecture is 3 hours. That's a lot of time to listen to someone even as fun as me talk, okay? Little pause, take a sandwich, some tea. We'll come back, we'll do the second part of the lecture, and then we'll crank out today's lab. So I'm gonna hit start, okay? And when this 25-minute buzzer is up, we'll come back. Sound good to you guys? All right. I'll see you in a little bit. Hello, Astronomy 1010. We're back. We're going to do part 2 of lecture 2, as much as I can do anyways. We got to do some stuff on coordinates. It's not particularly fun, but it's sort of necessary. And it's actually one of the more useful things you can learn in terms of if you're then going to go out after this class and take closer notice of the sky, as I hope you will, understanding how it rotates and understanding how it works can let you become a fun, casual observer of the sky. And you can point out your favorite things, constellations or whatever, to your friends. And people tend to like that stuff. So we need to draw some pictures together too. So I hope you guys have your art skills handy. Let me close this. We're gonna start with making a 3-dimensional picture of what's called our local sky. So I want us to basically draw this picture, and I want to define a few vocabulary terms for you. Let me show you how we're going to do that. So let me clear out my board. Give yourself quite a bit of room for this. You're going to need almost a full page. And this is going to be a 3D view of the Rhode Island local sky. This is about how to draw your local sky. Leave yourself some headroom here. Now, I'm going to take some measurements here because it improves the quality of the diagram. And if you guys did get a plastic ruler, I'm going to make some suggestions to you. Hold on a second. Oh, there's my ruler. If you do have a plastic ruler somewhere around, I'd say for a standard piece of paper, maybe 10 or 12 centimeters would be the ideal line. But I want you to draw yours about halfway down the page here. I've got more board to work with, so I'm gonna make mine about 60. I'm gonna make mine about 60 centimeters. And if you made yours 10 centimeters, then go ahead and mark the midpoint at 5 centimeters, okay? And now we're gonna try to draw a dome here. So I'm gonna make a 30 centimeter mark. You guys will be using a 5 centimeter mark. That should be the radius of your circle. Sometimes to improve my drawing of my dome, I actually take the radius, which for you guys might be say 5 centimeters, and I mark a few dots at 5 centimeters, kind of from the midpoint. This is just going to help you connect the dots and make a kind of very nice dome. One of the reasons you want to do this is a neat diagram helps you see the relationships between things. If you make a crappy diagram, it actually can end up confusing you more often than not. So I'm going to kind of draw my dome here. You can see by connecting the dots, I made a pretty decent, not perfect, but decent dome. Okay, if we want to 3Dify this thing, then let's put a dash above and below the midpoint of the ground, and let's kind of draw an oval in that connects the edges to those dashes. And you can see I've got myself a kind of a dome, a 3-dimensional dome here. I can even make it fancy and colorful. I could take some green and I could shade in the grass. Let's say we're standing out in a field. Keep in mind that you, the observer, are located in the center of the dome here. So we could put a small observing dude. All right, that's you, the observer. All right. It's really important when you draw these types of diagrams that you take some time to think about where north should be. Now, you can do it any which way you like, but since I am a right-handed person, I always tend to put north on the right-hand side. So that would make south on the left-hand side. East will be towards the board, and west will be in back of the board, okay? All right, so we've drawn our 3-dimensional local sky. Now it's time to identify a few key points here. I'm going to draw a line that goes through my observer, right through the center, up through the top of the dome. I'm going to label that with a Z. The point overhead is called your zenith. Another key vocabulary term is the horizon. The horizon is a 360-degree ring at the base of your local sky. And that means your horizon ring is right there. It's this black ring that we drew just a second ago. Another key vocabulary term is called the meridian. The meridian is an arc that rises due north reaches the zenith and sets due south. In other words, this is your meridian, okay? Now, I'd like you to remember that before tea break, I taught you guys that you can always see exactly 1/2 of the celestial sphere in your local sky. Therefore, check me out here. if I tiptoe forward here, if I'm in the northern hemisphere, like in Rhode Island, kind of like this person is, I should be able to see from my local sky everything in green here. So I should be able to see the north celestial pole in my local sky. I should also be able to see the projection of Earth's equator onto the local sky. So I should be able to see the north celestial pole and the celestial equator from the Rhode Island local sky. So I'm going to try to draw those in here, and I'll show you how we do that. I'm going to use a blue marker. And for the north celestial pole, I'm going to put it about halfway up the northern sky. I'm going to go from the foot of my observer, something like that, okay? Remember, I like to abbreviate the north celestial pole NCP. Let's also remember that the star Polaris is here. Okay, this is the hard part. The celestial equator is a ring that goes east to west, but it needs to stay perpendicular to the north celestial pole. I struggle with this personally, but what I like to do is kind of make a 90-degree mark here. And then I try to make like an arch that goes east to west. I'm not particularly good at this. That's about the best that I can do, all right? This is your celestial equator. And taken together, the zenith, the horizon, the meridian, the north celestial pole, and the celestial equator these terms are known as the fundamental positions of your local sky. They're called fundamental positions of your local sky. In other words, these are important vocabulary terms that I'm going to use and that you are going to use to help orient yourself and describe things on the sky. Otherwise, you're going to be saying stuff like, oh, it's the star that's just over the little pine crone on the tree. You can't do that kind of stuff. You need some fancy vocab words to talk intelligently about the sky. And these zenith, horizon, meridian, north celestial pole, celestial equator, that's it. Okay. Let me know when you're done with that. Whitney, let me know when you're done writing, because even though I just made this beautiful picture, I have to erase it now. I'm sorry, you good, Whitney? I just saw you writing. Nina, Nicole, you guys good?
Oh, I'm good, sorry.
You're good, okay. All right, I just don't, sometimes I erase too quickly and I don't want to do that. All right, I'm erasing now. Okay, now that you know what the local sky is, now that you know some terms, I'm going to talk to you about some coordinate systems. And these coordinate systems are going to help you identify how objects move through the sky. One of the coordinate systems needs to be a review of geographic coordinates. And that's because where you are on the ground determines what stars you can see in your sky. So for the rest of this class, we shall be concerned with 3 coordinate systems that we need to use in our astronomy class. Wow, I can't spell. Geographical geographical coordinates will tell us where we are on the ground or on Earth. The so-called horizon system, that's going to tell us where we are, where a star is on the local sky. And then lastly, the big buildup, we're going to use these in our labs today. The equatorial system, the most complicated, they tell you how to find things on the global sky or on the celestial sphere. Although the local sky is also the celestial sphere. But we're going to use these three things in different ways. I'm just having you take down this note so that you can, it's going to take a little while to march through these. So I kind of want to give you some top-down structure so you can see what I'm about to do here. All right. Hit hard return. Let's rewrite the term geographical coordinates. Hey, by the way, something to think about with geographical coordinates, horizon system, all of these coordinate systems, they're all angles. We tend to think of lines of latitude on Earth in terms of distance because that's how our brains are wired. But latitude and longitude are actually angles. Okay. We have latitude and we have longitude. Let's slap their definitions down, then let's talk about it. Latitude is defined as your degrees north or south of the equator. Longitude is defined as your degrees east or west of the so-called prime meridian. All right, let's chat about that. Earth is a ball, but it's a spinning ball, and that gives it some symmetry. If the Earth spins on its axis, the equator is a unique point because the northern and southern hemispheres are kind of symmetrical to each other. This makes the equator a natural place to begin our coordinate system. Lines of latitude go like a ladder, but they measure north to south. If you're on the equator, you're at 0 degrees latitude. And from there, you've got to march upwards. If you are in Guatemala, you're 15 degrees north. If you are in Tucson, Arizona, you're 30 degrees north. Our own beautiful state of Rhode Island is about 42 degrees north of the equator. Let's put that down here on the side. So for Providence, Rhode Island, this is going to be necessary for our homeworks as well. Our latitude is 42 degrees north. You've got to specify north or south unless you're on the equator. Longitude is kind of funny. Lines of longitude run like tangerine slices through the Earth. They run north to south, but the purpose is to measure east to west. Unlike latitude, which has a natural symmetry point, there is no one tangerine slice that is superior to any other to begin measuring longitude. So humans had to invent where the 0 point of longitude would be. And here's what they did about that. They actually chose for the 0th line of longitude, a longitude that runs through the city of Greenwich, England, right through the front door of the Royal Greenwich Observatory in England. And this line that runs through the front door of the Royal Greenwich Observatory is called the prime meridian. After that, you carve the Earth up into a Western hemisphere and an Eastern hemisphere. In fact, you can go and do a little nerd tourism. You can visit the prime meridian and you can stand with 1 foot in the Western hemisphere and 1 foot in the Eastern hemisphere, and you can take a selfie and post it to Instagram or something, okay? And that's a thing that people do. In fact, one of my former students did this, and they brought me as a gift my very own prime meridian pencil from the Royal Greenwich Observatory gift shop. And my prime meridian pencil is a treasured item. I don't let anybody borrow that, okay? So if you measure Providence, Rhode Island from the prime meridian, we're 71 degrees west. What's
That's
the latitude? Go ahead, Nina.
Sorry, is that a 71 or a 74? 70.
71, sorry.
No, it's okay. I just wanted to clarify.
Let's have you guys try it. What is the latitude of the North Pole? Practice. Prove to me that you understand latitude, longitude. What's the latitude of the North Pole? Ha. I thought this was easy stuff. No one can tell me the latitude of the North Pole? Whitney?
50.
Jeff?
90 degrees.
You're missing something. You're almost there.
90 degrees north.
That's what I need to hear. Otherwise, it's ambiguous. Remember, Whitney, that the North Pole is perpendicular to the equator, right? If you're here at the equator to go up to the North Pole, that's a 90-degree angle. That's a right angle. Okay. Jeff, hotshot that you are, I got one for you here. Jeff, what is the longitude of the North Pole?
Oof. 69. Got me there.
Anyone?
Is it 0?
180.
Nicole, it's not that you're wrong. It's just that you're not entirely right. There's a bit of a problem up here at the North Pole. Can you guys see what it is? All lines of longitude pass through the North Pole. So yes, the longitude is 0 degrees. Yes, it's also 180, and it's also 270 and 271 and 51. In fact, it's not well defined, it's undefined. Mathematicians have a name for such a point. They call a point like this degenerate. A degenerate point is a multi-valued point. It's one which does not have a clearly defined longitude because all the longitudes are passing through it. And that's just part of the nature of the beast of designing a coordinate system on a curved surface. There's actually a kind of higher order math thing going on here about curved coordinate systems and degenerate points. But let's just mention that not every point has a longitude. The North Pole, its longitude is undefined or degenerate, to use a mathematical term. That's okay, though. The reason why it's okay that the North Pole is degenerate is because if I tell you, hey man, I'm at a latitude of 90 degrees north, you know that there is only one place on Earth I could be. I'm hanging out with Santa Claus at the North Pole. On the other hand, if I tell you that I'm at a latitude of 30 degrees north, it does not have the same advantage because it could be Tucson, Arizona, it could be Atlanta, Georgia, it could be, what is this, Baja, California? I don't know. There's a whole bunch of different places at a latitude of 30 degrees north, but there is only one place at a latitude of 90 degrees north. So even though it's degenerate at the North Pole, the latitude compensates for it. Just some things you didn't know about coordinate systems. Let's talk about some other things you don't know about. Do you guys know there's a thing opposite the prime meridian? Do you guys know what the name is for the line that's behind the prime meridian? It's called the international date line. And that's important from the perspective of timekeeping in astronomy, because if the Earth is constantly spinning, you have to decide where the day begins, because the sun's always shining somewhere, right? We define the beginning or the start of a day as being at the international date line. And for a couple of good reasons. So, you know, if you're like a businessman and you fly from Tokyo to California, you might end up crossing the international date line and kind of going back a day. You could accidentally fly from Wednesday to Tuesday. One of the reasons why the international date line does this little wiggle is because the international date line is pretty good over here because there's not a lot of land mass. You wouldn't want the international date line to cross through like a major territory, because then the postman would be miserable because it would be like Tuesday on one side of the street and Wednesday on the other side of the street. And that could make for some messy issues, right? So it kind of does this little wiggle around Alaska and Russia, and it kind of bumps around Fiji and Tuvalu and some other places. But for the most part, it kind of crosses through mostly nothing, okay? Cool. I'm going to erase this now. Now that you know how to find yourself on Earth, oh, wait, one more fun show and tell. This is just for kicks. It occurs to me it's kind of fun that these iPhones, they come with a little compass app if you have one. Let me see if I can focus my screen. I think 50 is pretty good, somewhere around here. Let me see if I can find, where did I hide my compass app? If you go, I don't know what the equivalent is in the Google phone, but if you go to your compass app, it actually gives you your latitude and longitude to a very high degree of precision. And I think this could make for a kind of jazzy show and tell for a second. Check me out. So I'm in downtown Providence right now. And let me find where it's best in focus. Look, what are those things there? Let me see if I can get a better focus. It looks like I'm at 41 degrees north latitude. What are these things over here? What's this 4923 all about? What's going on there, kids? Talk to me. What are the other numbers?
Are those like the exact specifications of your location?
Yeah, but they're broken down into what? It's 41 degrees,
Oh, arc minutes?
Minute?
arc minutes and arc seconds. Remember, latitudes and longitudes are angles. You can see they're using arc minutes and arc seconds there, right?
Yeah.
So I'm at 41 degrees, 49 arc minutes, and 23 arc seconds. My longitude is 71 degrees, 24 arc minutes, and 44 arc seconds. Why doesn't someone else open up their phone? Let's see who's close to me and who's far away. Whitney goes to some of my stomping grounds, so I suspect she's in Providence too. What do you got, Whitney? Do we have any differences there?
Yeah, I have, oh wait, hold on, see?
Read me yours so that
Wait.
everyone can compare. What is your exact numbers?
Sorry, all right, 1-7, I keep changing
No,
so
no, no.
fast.
You want to give me the north and the west.
Sorry, all right, so 41, 51, 26.
71, 29. So we are 3 arc minutes apart from each other, and we're about 4 or 5 arc minutes of longitude away from each other. Are you in
What is-
Providence?
Johnston.
Oh, you're in Johnston. So just the distance between Johnston to Providence is a difference of 2 to 3 arc minutes and maybe 4 arc minutes of longitude. A few arc minutes of latitude. How about someone else? Is anyone down like in South County?
What's that relative to? Is it arc minutes relative to the pole?
No, well, I just answered that question in our notes.
Yeah.
It's relative to the equator for
The equator.
latitude,
Okay.
and it's relative to the prime meridian for longitude.
Gotcha.
So this, for instance, means I'm 41 degrees above the equator, but I'm also an extra 49 arc minutes, which is almost a whole nother degree, and I'm 23 little arc seconds. You know, there's a problem in the book where we have to work out how many kilometers does a degree of latitude equal? How many kilometers does a arc minute equal? How many kilometers? I should assign that problem. That might be useful. All right, just fun things. You can look up your latitude right here on your phone. Let's talk next about how to find objects on our local sky. There's a really basic coordinate system that's easy to use called the horizon system. This means we're going to measure the position of a star relative to the horizon. We have 2 angles. One is called altitude. The other is called azimuth. Altitude is defined as your degrees above the horizon. And if you want to get technical, it's degrees above the nearest point on the horizon. Azimuth is degrees along the horizon measured clockwise from north. Let's take a peek at that. Here we go. So here's a dude. Actually, I don't know if I like this picture because we've rotated north. Since I can scribble all over this stuff now, why don't we go back to our groovy little local sky thing here, okay? And let's imagine a random point, okay? Like a point over here, this purple dot, okay? To find the altitude and the azimuth of this dot, I need to use the definition. So I draw an arrow up to here. Now, the altitude is the degrees above the nearest horizon. It's a little ambiguous where, but it kind of looks to me like if I were to go down the globe, let me try to undo that here. Let me try to draw that a little better. If I were to go down that curved globe, it's hard to draw with your mouse. Something like that would be my nearest horizon. And it looks like, I don't know, the angle that this makes here is greater than 45 degrees. I'd say maybe the altitude is like 60 degrees. I'd say that that little purple star is about 2/3 of the way up the dome. That's its altitude. To get the azimuth, you have to go clockwise from north. So you start at north. It's, oh, shoot. And then you go clockwise here. What would you say? Give me a reasonable guess. What would you say the azimuth of that purple star is?
45 degrees.
Yeah, maybe 45 degrees, something like that. Okay, good. That's reasonable. Let's try a couple of other tests here to see if we understand. Let's take the zenith. What is the altitude of the zenith? What is the altitude of your zenith? Nobody can do that? Okay, let's take a step back. What is the zenith?
It's the point overhead.
Okay, so you know that.
Yeah.
Can you use the definition to get me its altitude? What's the definition of altitude?
The degrees above the nearest horizon.
So how many degrees above the horizon is the zenith?
180.
180 is half a circle.
Yeah.
There's no such thing
Oh, okay.
as an altitude of 180.
Yeah.
How many degrees is it from, say, here up to there? I thought that would
90?
be, yeah, 90 degrees, right?
Yeah.
Do you guys know perpendicular lines, when two lines meet and make a capital T? Have you ever heard that before?
That's old school.
Yeah, and what I'm saying is, so is right angles. They're like 500 BC old school. This is a 90-degree angle. All right, whatever. The altitude of the zenith is 90 degrees. What about the zenith's azimuth? What is the you know, it's one thing to listen to someone talk. It's a totally different thing to use your brain and answer questions. Much harder to do that. That's what we must practice at. What is the azimuth?
360?
We measure clockwise from north. So 360 means you go all the way around the ring and back. So why did you say 360 and not 0? They're kind of the same thing, right?
Yeah, I was looking at the plane.
So this is your zenith right here. What's the closest point on the horizon to the zenith?
90 degrees.
90 degrees would be, so let's use yellow for your azimuths. That's an azimuth of 90 degrees. That's an azimuth
Oh,
of 0 or 360. This is an azimuth of 180. This is an azimuth of 270.
that's it.
Which of these 4 yellow points is closest to the zenith? Give up? All of those points are equally distant from the zenith. Every point on the horizon, whether it's there or there or there or there, are all equally distant in angle. Every point on the horizon makes a 90-degree angle with the zenith. So what can we say then about the azimuth of the zenith?
It's undefined.
That's right, it's degenerate. Checked you. All right. I've got more to say about this, but I really have to get to my last coordinate system before we run out of class time. Why is the altitude azimuth system used, and why is it not enough? Well, it's used because it's simple and it's easy, although you guys might not think so. Let me tell you about a telescope that really gives me the willies, cold chills, just thinking about a plane wave 1 meter telescope. If I could have anything for Christmas, it would be a plane wave 1 meter telescope. It's a gourmet observational telescope that you can do serious research with. It's only $500,000. So if you have any rich uncles or friends that want to donate to science, have them hit me up. Okay, now this bad boy here uses what's called an altitude and azimuth mount to stare at the sky. Let's see if we can find a YouTube video of plane wave 1 meter telescope. They have a little YouTube video of this thing in the clean room here. Yeah, this is what I see. So here it is slewing around, pointing at the sky. Watch how the two things rotate. So right now you can see the telescope moving up in altitude, right, on those fork arms. But meanwhile, it's also swiveling around in azimuth. Now it's pointing up to the zenith, okay? And now it's swiveling entirely in azimuth, right? And now it's probably going to kind of point down again. This is called an altitude azimuth mount. It uses the same coordinate system that you just discovered. The reason why you would use this is if you were out at the telescope with your Grammy, you could say, Grammy, you know, I need you to point the telescope at the Orion Nebula. And she's going to say, I don't know where the Orion Nebula is. You say, oh, that's easy, Grammy. It's 30 degrees azimuth, right? So you swing 30 degrees. And it's 45 degrees altitude. And then you can point your telescope right up to the Orion Nebula. The reason why, so that means that the horizon system is real good to use when you're messing around with your buddy at the observatory in your local sky. There's two issues with the horizon system. Let me show you what the first one is. During the course of the night, the sky is going to rotate. Just like the sun rises and sets each day, stars rise and set each night, and they do so in a sort of complicated way, as slide 68 demonstrates. If you are standing in a field at night, as Earth spins, stars will rise in the east, they will come up in your local sky and cross your meridian at the highest point of their journey, and then they will sink back down into the west. And they're doing so at kind of a sort of sloppy angle here that depends upon your latitude. So first of all, the horizon system is rough because if you point your telescope at the moon and you don't have a tracking mount for it, the moon will just rotate right out of the system. The second issue is, what if you discover a new nebula and you want to name it after yourself? You want to call it the Whitney Nebula or something. So you call up the International Astronomical Union headquarters, which might be in Tennessee or something, and you say, hey, you know, I found a new nebula. It's called the Whitney Nebula. I want to name it after me. They're going to say, well, where is this nebula, Whitney? And you're going to say, oh, that's easy. It's at an altitude of 42 degrees and it's at an azimuth of 30. But then you start shaking your head and saying, geez, if it's at 42 degrees altitude for me, is it going to be 42 degrees altitude for someone in Florida or someone in Tennessee? I don't think so, because as you change your latitude on Earth, the positions of the stars will shift. And that means your horizon system is only good if you're in the exact same location as someone else, namely Rhode Island. If you want to talk to other astronomers around the world about the cool quasar that you discovered, it's not helpful to use the horizon system. What we need is a set of global coordinates for the sky, something that doesn't depend upon where you are on Earth. In fact, what we really need, what we're going to be using in our labs today, is we need kind of like latitude and longitude, except for the sky. And that's where our third coordinate system comes in. The idea is once we put a star, we can give it a set of coordinates, and in theory, it should not change. This, my friends, is the big kahuna that we've been working towards all day, the equatorial system. It's also wicked freaking confusing. Okay. Introducing the equatorial system. These are coordinates that are good for sort of a global sky framework, all right? It's kind of like latitude and longitude for the sky. It uses two angles. One is called declination. The other is called right ascension. And astronomers have abbreviations for these things. Declination is sometimes just referred to as dec, or sometimes we even use a little delta for declination. Right ascension is often abbreviated as RA. They have kind of funky definitions. Declination is kind of like the equivalent of latitude on the sky. Right ascension is kind of like the equivalent of longitude on the sky. Now, let's do some good remembering here. Students, how did we define latitude just a few moments ago? What's the definition of latitude?
The degrees north or south of the equator.
Okay, so that suggests how we might do things on the sky, right, Nicole?
Nina.
Oh, sorry, Nina. I was trying to
Okay.
guess. I was looking at one of my little feet fell off here.
No worries.
Nina,
Yeah.
it suggests that our definition for declination should be, for the sky, we do not use north or south. By convention, we use positive or negative. Degrees, positive or negative from the celestial equator, because we're on the sky now. Okay. What about right ascension? How did we define longitude when we did it for Earth?
Degrees north or south.
No, this is longitude now.
Oh, I'm sorry, I was reading the wrong one. East or west.
East or west from what?
The prime meridian.
Yeah, so we have this prime meridian that goes through Greenwich, England. Where are you, Greenwich, England? Right? And then we measure degrees west or degrees east from the prime meridian. The prime meridian is not going to be useful to us here. And let me show you why. I could take this globe And I could adjust the ring here so that the ring is lined up with the prime meridian. Let me go ahead and do that. Okay. Notice that inside my globe, I've roughly lined that ring up with Greenwich, England. During the course of the night, or during the course of the day for that matter, as Earth spins, the prime meridian will also spin and point to different positions on the global sphere. We do not want a rotating coordinate system. That's all kinds of crazy business you don't want to get into. We need to pick a point that is somewhere fixed to the celestial sphere to be our prime meridian. And you're not going to like this one bit. Earlier in today's lecture, I told you guys
Yep.
that the spring equinox is a point on the sky. Let's try to take a look at that here. Let's look at, where are we? Whew. I thought here we go. Suppose you look at Earth, but you tilt Earth so that the North Pole isn't really up. You're kind of tilting it so that the ecliptic is horizontal. Here I'm using definition number 2 of the ecliptic, which I am willing to bet $100 million everyone has forgotten. But in any case, you'll notice that, actually, no, never mind, I can't tolerate it. Someone look up the definition number 2 of the ecliptic and read it to the class, because you've all forgotten and I already know it. What is the ecliptic in this context? I can't make you memorize it, but I can make you read it.
It's the path of the sun against the background stars, also known as the zodiac.
Right. And this is also the plane of the solar system, right? That's the Earth-Sun kind of line. It's the path of the sun. Okay. So I've kind of tilted the Earth so that it's 23.5 degrees off from the ecliptic. And that makes the ecliptic horizontal, which is kind of cute. Notice that I can think of the spring equinox as a point on the sky. The spring equinox is a point where the celestial equator intersects the ecliptic. And that point is a real point on your sky that rises and sets every single day. Let me show it to you. Huh. There's something funny about this slideshow. It doesn't have, what am I doing wrong here? I got the wrong damn, hold on a second. 1020's got a little more on the ball here. Sorry guys, just a sec. Yeah, 78. Okay, the spring equinox is a literal empty point on your sky located somewhere in the constellation Pisces. Every day at some time or night, day and night, the spring equinox rises just like any star would rise or set, and it travels through your sky. You've never noticed the spring equinox before because there's nothing there to see. Well, most of the time there's nothing there to see. Once a year, once every year, a very special star will appear at the spring equinox. Anyone want to take a guess what that star is? The special star that appears once per year at exactly the point of the spring equinox? Anyone get my drift here? No? No? What if I if I change my colors here. A very special star that appears once every year at the spring equinox. Wow. It's the fucking sun. The sun will be at the spring equinox. Let me tell you what day it's going to be there. You'll never guess this one. March 21st. And let me tell you where the sun's going to be on June 21st. It's going to be here at the foot of Gemini. That's kind of the whole fucking point of the equinox, right? And let me tell you, on September 21st, the sun's going to be over here in Virgo. And that's where the sun's going to be, right? There, all of these concepts that we talked about today are connected. The equinoxes and the solstices are points in the sky because that's where the sun is going to be on those days. Wow. Okay. Well, that didn't go so well. Let's try this one on for size. Do you know that we could measure angles on the sky, not only in terms of degrees and arc minutes and arc seconds, but if we were really insane, we could even measure them in terms of hours. And of course, because we are insane, that's exactly what we're going to do. Let me put this one in your pipe and smoke it for a second. Okay, so here's the spinning Earth. And the Earth spins on its axis in 24 hours. And in 24 hours, the Earth is going to rotate through a 360-degree circle. And that means the sky is going to spin by 360 degrees. Something interesting happens when you divide 360 degrees by 24 hours. Go ahead and do that. Divide them up with your Casio calculator. Tell me what you get.
15.
Exactly 15 degrees per hour. That is not random that worked out so beautifully. That's intentional. The ancient Babylonian astronomers, they designed the hour in such a way. They divided the sky up into 15-degree segments and they called them hours. This means in astronomy class, there's a weird kind of conversion factor that normally wouldn't make sense anywhere else. 1 hour is equal to 15 degrees of sky rotation. That's a key point. In astronomy, 1 hour is equivalent to 15 degrees of sky rotation. And because of this, we're going to use this to measure the position of stars in hours rather than degrees. Okay, you're finally ready to learn the right ascension definition, okay? So write all that down. Okay, here goes the definition of right ascension. It is the hours and minutes of a star measured eastward from the spring equinox. Class, remind us what eastward means, those of you who come to class and pay attention and listen to me. What does eastward mean in astronomy?
Clockwise?
Where's my shotgun? I'm gonna go blow my brains out here in the kitchen. It's backwards. It's eastward is counterclockwise, okay? Never forget, eastward is counterclockwise. At least you remember the concept, Nicole. That was something. Okay. Are you ready for this? No, probably not. But this is the basis of our lab today. Let's just, before we do our lab today, because I know this is going to help us a little bit. let's try a quick practice problem. You can even, this is actually kind of a part of your lab, so I'm ironically doing a little bit of your lab right now. What I want to do to prove that you can handle this is I want you guys to give me, think about this. If the spring equinox, the summer solstice, the fall equinox, and the winter solstice, if they are all points on our sky, we should, in theory, be able to describe them each with a right ascension and declination. I want you guys to try it based on those definitions I just gave you. And no, this is not going to be easy. That's why I'm making you do it. I'm going to now erase this, okay? Here I go. Okay, last little bit of notes here. Here's an example. Find the right ascension and declination of the 4 key points in Earth's orbit that we talked about today. We'll start easy with the spring equinox. We need a right ascension and we need a declination. Can anyone out there give me either of those 2 coordinates? And if you want help, you should regurgitate your definitions and look at this picture. So I want someone who could either give me the right ascension or the declination of that point. Nicole's looking at her definitions here. Nicole, which one do you want to try? Try one. Right ascension or declination? Nicole, the definitions were just given to you a second ago, right?
I know my notes are messy. I don't know where they went.
Dude, how can your notes be
Give me
so
one
messy that you
second.
don't know what you wrote down 5 seconds ago? Look under equatorial coordinates. You're flipping
Okay,
it.
found it.
Okay. You're scaring me here. All right, you're scaring me. What's the definition? I think declination is easier personally. What's the definition of declination?
Degrees positive or negative from the CE
Celestial equator. So can you tell me how many degrees positive or negative that point is from the celestial equator? First of all, Nicole, note that it's like on the celestial equator. That's, you know, it's on the red ring, right?
Yeah.
So
So it would. Is it undefined?
no. It's well defined, very well defined.
Okay. Is it 90?
No. It's degrees above or below the celestial equator. And it's like on the celestial equator, right?
So is it 0?
That's right. It's 0.
Okay.
Because this is on the celestial equator, so it's 0 degrees above or below, right? Okay. Woo. So the declination of the spring equinox is 0 degrees. All right, someone else try one. Nina, why don't you try the right ascension? What's the definition of right ascension?
Is it hour 2 minutes of a star?
Hours and minutes.
Hours and minutes of a star measured eastward from the spring equinox. Sorry, no. Yeah, that was right.
Okay, so how many hours off of the spring equinox are we?
0.
That's right, because you're on the spring equinox.
Yeah.
And normally the way right ascension works is they're like tangerine slices, but you measure them eastward or counterclockwise all the way up to from 0 to 24 hours. If you're on the spring equinox, however, your right ascension is just 0. So very good. Now, Here's how we write ascensions. We write them like military time. All right. Let's try the summer solstice. Looking for a right ascension, looking for a declination. Whitney? Whitney, can you give me either the right ascension or the declination of that point?
I don't know.
Why don't you try declination? I think that one's easier. What's the definition of declination?
The degrees, positive or negative from the CE.
Okay, so is it positive from the CE or negative from the CE?
Positive.
Yeah, because it's going up in this direction. How many degrees positive? Psst, it's on the diagram.
Oh, 0.
No.
23.5.
Yeah, look, 0 would mean it's on the celestial equator. This angle tells
Oh,
you it's
okay.
positive.
I thought,
Positive 23.5. Okay. So we have the declination is positive 23.5 degrees. What about the right ascension? How many hours is it from here to there? How many hours does it take to go around the entire sky?
24.
How long does it take to go half of the sky?
12.
So noticing that it's a quarter turn, the right ascension must be
6.25.
no, not 6.25, but
12.5.
no. 12.5 would be like over here.
Is it 6 hours?
Yeah, 6 hours, because it's a quarter of a turn around the clock. A quarter of 24 is 6, right? Oh, today's lab's going to be fun. I can already tell. Okay, so then we have the fall equinox. Are you guys picking up on what I'm putting down yet? Someone give me a right ascension or a declination for the fall equinox. Anyone at all, I don't care. Anyone who does anyone understand me? I'm starting to get nervous that nobody understands me. It's lonely up here. Right ascension or declination of that point.
0.
For
Or
which
0
one?
hour. The right ascension is like 0 hours.
False. Right
False.
ascension is measured eastward from the spring equinox.
Yeah.
You are definitely not on the spring equinox.
Yeah. Sorry.
So is
Try
it
again,
12
Nina.
hours?
It's 12 hours right ascension. Very good. How about the
Yeah.
declination? How about the declination?
0.
0, because it's on the celestial equator. Nicely done.
Wait, the right ascension was 12. Yeah, you just write it down. Okay.
Can anyone give me the winter solstice without even looking at the picture?
$12.
Not 12. Remember, 12 hours is half a turn. That's 12 hours there. But the winter solstice is 3/4.
Oh,
18?
That's right. 18 is the right ascension. What's the declination?
-23.5.
Say that again.
Negative 23.5.
Very good, Nina, with the negatives. So it's 18 hours negative. Okay. That ought to help us during the course of our lab today. Well, you've done it again. You've burned through another lecture with me, another 3 hours of grueling astronomy. We learned a lot today. It's now time for lab. I'm going to try to keep it short and sweet, but we got lab to do because it's a lab science course. We're going to use that there celestial sphere. I'm going to need a minute to set things up, but here's what I think you ought to do. Let's go to our second lab, which I think I forgot to activate. Let's get out of this YouTube video here. Okay, let's cut this stuff down. This ought to speed up. Oh, I want that. Save image. Oh, sorry. That was a pretty cool, the obliquity of the planets. We won't forget about that anytime soon. Yeah, okay. I don't want to lose that guy. That's pretty cool too. Okay, we did a lot today. Let's go over here to lab. We're going to do lab number 2. This will be the third thing that you owe me this week. So if you're new to hanging out in our class like Mellow Yellow over there, you got some work to do if you haven't turned anything in yet, okay? You owe me lab 1, you owe me homework 1, and now you're going to do lab 2 with me. Let's make it available. Sorry, I meant to do that earlier, guys. Okay, you now have access to the Celestial Spheres PDF. And why don't we go ahead and print this? We're not going to do all of this, okay? So why don't you print the first 2 pages? That's the most we're even going to have time for. So just hit print and choose pages custom 1 to 2. And I'm going to pause the recording while that prints. And I'm going to take my computer over to the lab area where we are going to do lab at the desk. Okay? Sound like a plan? So give me about less than 5 minutes. I just need a few minutes to set my computer up and I'll be right with you, okay? Go ahead and print that out. If you don't have a printer, you're going to have to copy that out by hand, so get going. Sorry, we're back here and we're about to do lab number 2.
Yeah, yeah. Go lay down.
Jeff, I'm going to mute you. Someone just asked me a good question, so I wanted to get that into the recording. Someone just said, hey, brother, I'm having a printer problem, and I'm having trouble printing out the first 2 sheets of lab number 2. Well, I suggested to them that since today's lab isn't going to be super mathematical, they could choose Open and Acrobat for their PDF. That's for lab 2. And then you can choose Fill and Sign, and you can write the name of the star here, okay? So that's one way and then you could save it as a PDF and you could submit it to me. At that point, Nina asked, do I have to submit all the pages? And my answer to her was no, you only have to submit those pages that we write on. In today's lab 2, which is this lab here, it's on using the equatorial system and measuring some positions of stars. We're probably going to do the first page and maybe the second page here. And I think that's all we're going to have time for, because that's going to take a wee bit of time. I'm going to need my celestial globe. I just thought about that.
I don't know how I made myself on the bigger screen.
Okay, let me explain that to you. Who's talking right now?
Oh, Kyle, Mellow Yellow.
Oh, Mellow Yellow. Mellow Yellow, could you change it here?
I don't know how to change my name. I want to change
Okay.
it to Kyle Maloney because that's my name.
Kyle, I'm going to change it to
But-
Kyle. Thank you. Yeah. Okay. So, Kyle, there's a button in the upper right corner that says View. You can toggle between Speaker View and Gallery View. You're probably in Speaker View right now, and you've double-clicked yourself. So if you double-click my face, scroll along the top boxes until you see my face, double-click my face, and you should see me appear much larger. If you want to see what everybody else is up to, go to Gallery View. Does that work?
I can't see it for whatever reason.
Sorry
Sorry
I want
about
to help
this.
you, but I can't show you my screen in a weird way, and you can't show me your screen. Actually, no. Kyle, I'm going to show you what to do. this is related to how we're going to prosecute lab today. I am going to use this as a remote camera so we can execute lab 2, and I'll show you how I do it in my screen. Okay, Kyle? So let
Okay.
me go to share, iPhone, share. And now, oh shit. What the hell did I do? Okay, there we go. Just a sec, guys. I should still be able to connect to wireless. I'm sorry, guys. Hold on. Yeah, I'm still connected to wireless. Okay. This is a, I can use my iPhone if I really have to, but gets a little personally invasive. Come on, you bastard. Okay, I know I'm going to end up regretting this at some point, but I'm going to use my phone. And I'm definitely going to regret this. Okay. In any case, there we go. Let's see if this works any better on my more modern. Oh, yeah. Okay. Sure enough, this is going to be the death of me right here. This is how I get fired. Okay. Here we go. So now you guys can see what's going on. So let's get back to Kyle's question for a second. Kyle, I got to get rid of. Oh, I'm in share mode. I guess, Kyle, what you have to do is you have to find my face and double click my face, but you can kind of toggle between like gallery view. It looks a little different when you're not in share mode, but just, I don't know, play around with the buttons. You're going to figure it out. Okay. The important thing is, can you see my paper here? Can you guys all see this thing? My
Yep.
pencil? All right. So let's start by doing our labs here. Let's put our names down, okay? This is lab number 2. It's very important that we label this lab so that you know where to submit it. This is lab number 2. This is the 3rd assignment that you owe me this week. A reminder to the class who is finally watching the videos, each week your homeworks and labs are due by Sunday at 11 p.m. At that point, I'm gonna close out the books and make it too late. And it'll be a 0 because I have to actually do this stuff. All right. You guys are in Astronomy 1010, so let's also label that. Okay, in Table 1, they've identified the coordinates, right ascension and declination, of the 10 brightest stars in the sky. They're the most famous stars in the sky. Our job is to identify the star and identify the constellation using that celestial globe. Now, this is a really cool lab when you do it together in the lab room because it's kind of fun to play with these globes, but COVID-19, blah, 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 there's nothing we can do about it. Let me tell you a few things that you might want to know about constellations before we proceed. Constellations, and I don't want to leave this share mode because I might end up regretting it. Do you guys remember how many constellations cover the nighttime sky? I told you in our first lecture.
18.
88.
88. Give yourself a cookie. Constellations are not just the stick figures, but they represent areas of the sky. So the International Astronomical Union blocks off all the region of the sky around Orion, and that's all considered the constellation of Orion. If I discover a galaxy here, that's considered in the constellation of Orion. So in this way, the entire globe, it's kind of like a map of the United States. If you throw a dart at one of those Sorry. I'm trying to make sure that my computer screen, here we go. If you throw a dart anywhere at this globe, you're always going to be in one of the 88 constellations. And let's take a look at how this works here. Here you can see you're in the constellation of Andromeda. These blue lines are the stick figures of Andromeda. These things are the stars. This star, for instance, is called Alpheratz. I'll explain why it's backwards in just a moment. The boundaries of the constellations are the dotted blue lines. So we're going to have to pay attention to that throughout the course of today's lab. Here's the celestial equator. That has a declination of 0 degrees. Here's the North Celestial Pole, where Polaris is. Actually, the way that you're supposed to do this, they want to represent the curved geometry of the sky. So you're supposed to kind of look through the globe and then use like a baffle to read the names of the stars. I guess I can do it like that. I kind of find it's just easier to read it all backwards, personally. Okay. Let's look for declinations and right ascensions. So this looks like it's the spring equinox here. Okay, so if this is 0 degrees declination, we're on the celestial equator, that's +10, +20, +30 degrees declination. You can see the hours of right ascension are listed here. That's 1 hour of right ascension. All of that is 1 hour of right ascension. Sorry, that's 0 hours of right ascension, excuse me. This is 1 hour of right ascension, that entire tangerine slice. This tangerine slice here, 2 hours, is all up and down there. And it goes all the way around the globe. Our first job today is to locate a star located at 6 hours and 43 minutes right ascension and -17 degrees. Let's see if we can do that. We're going to scroll around. Here's 5 hours of right ascension. Here is 6 hours of right ascension. Now, oops, it looks like we've got some minutes kind of ticked off here, right? Let's see. 1/3 of an hour is 20 minutes. So that's 6 hours and 20 minutes. That's 6 hours and 40 minutes. If I take 20 minutes and I divide it into 1, 2, 3, 4, 5 boxes, each of these little tick marks is 4 minutes. So to get to 6 hours and 43 minutes, I'll stay on the celestial equator. I'll go 6 hours, 20, 40. And that's 6 hours and 44 minutes. So I should be sort of parallel with that line there. Now I'm supposed to go -17 degrees. So I'll go down -10, down -20. And what is my star?
Sirius?
Sirius. And the constellation?
Orion? No.
No, it's close to Orion, but it's not an Orion. That's the constellation there. See the boundaries? The name of the
Yeah.
constellation is right there.
Well, your letters are backwards.
Canis Major.
It's backwards for me too. You channel your
Oh.
dyslexia. Canis Major, the big dog. So of course this is going to be the first star. You'll remember from our lectures that Sirius is the brightest star in the sky. In fact, it's known as the dog star because it's located in Canis Major, the big dog. Okay, let's move on. 7 hours, 37 minutes, +5 degrees declination. Okay, so we're pretty close. There's 7 hours. I would say 37 minutes is pretty close to 40. So let's just swing 2/3 of the way over here. The declination is +5. Bloop, 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 bloop. What do we got?
Procyon?
Procyon, very good. And what's the constellation?
Canis. No.
Minor. That's minor.
Canis Minor, the little dog. And this is Procyon. Sirius and Procyon follow at the heels of Orion as he marches around the sky. They're like the little hunting dogs that follow him. legendary constellations. Procyon. In ancient Greek and Latin, C's were pronounced like K's. Procyon. And that's Canis Minor, the little dog.
Those are the dippers, the Big and Little Dipper.
No. The Big and Little Dippers are found up here near Polaris.
Oh, gotcha.
They're part of, the reason why you're getting them confused is the Big and Little Dippers are Ursa Major,
Oh, that's
Ursa
why.
Minor. They're
Gotcha.
the bear, Big Bear and Little Bear. That's what you're getting confused on. Okay,
Thank you.
Ooh, I cannot break this globe because it's $500 and I can't replace it. And they don't make them anymore, actually. Oh. It's a kind of a concern for me. 20 hours and 40 minutes, positive 45. Okay. So let's keep rotating around here. I need more hands. What I need is the tape. Okay. Maybe, we'll see. Unfortunately, Jordan, I might take you up on that, but right now it's hard to explain where I want to point at all moments. Okay, so I've rotated over here to 20 hours. How many minutes, guys?
40.
40.
Okay, so there's 20, 20, 20, 40. I want to make sure I start at the celestial equator before I measure any declinations. Okay, what's my declination?
Positive 45.
Positive 10, positive 20, positive 30, positive 40. What's my star?
Neb.
Deneb. And can you say that? CYGNUS. Cygnus the Swan. Deneb is the tail feather of Cygnus the Swan. Cygnus is up all throughout the summer. It's part of the summer triangle. Oh, sorry, I spelled that wrong. CYGNUS. I recommend pencil for these labs for reasons that should be obvious. Sorry about that. Okay. So that's Cygnus the Swan. 1948, positive 9. 19, 40, 44, 48. Positive 9 is here. How do I say that?
Altair.
Altair. And the constellation is Aquila, the eagle. Aquila, the eagle. Star name is Altair. And it's Aquila, the eagle. Hopefully you guys can see this okay. All right. 1513, positive 46. So 15, 4, 8, 12, 15, 13. Positive, what was it?
513.
Oh, wow, I'm dumb. Okay, so let's go to 513 instead. Whoops, I lost it here. Okay, 5, 13, and positive 46. 10, 20, 30, 46.
Capella? No.
Capella.
Is that
And
the,
pardon?
that's a star name, right?
Sure is. That's the name of the star. And let's look at the boundaries of the constellations. We seem to be connected to this guy here.
Arugia? Oh, no.
Auriga.
Riga.
Auriga is the herdsman, and Capella is the goat on his back. Okay. So Capella, very bright star in the nighttime sky. Probably see that overhead tonight, actually, if the sky is clear. Okay, 513, -8. 513 -8. This one's a little bit confusing. You can see that these stars are part of the constellation of Orion. This is one of the feet of Orion. It's called Saiph. But this star here is the one we want, because that's 513, -8 is Rigel. Rigel is the blue lower foot of Orion. That's star Rigel in constellation Orion. I'm going to skip this one for a moment because I'm already around 5. I'm going to do 553 and +7. So 553 is almost at 6. +7. What do we got?
Beetlejuice, you guys?
Betelgeuse. And that's also in Orion. Make sure you skip one here. Okay. Now I can jump ahead to these guys. Let's go to 1410. 1410 is like there, 4, 8, so that's 1410. And then +19, +10, almost 20. What's our star?
Arcturus.
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 And the name of the constellation is kind of up here. It looks like a necktie or something. The constellation, it looks like booties, but it's Bootes. Bootes is also a herdsman. And Arcturus is, I don't know, his foot or something. Okay. So Arcturus in Bootes. I believe one of the O's has an umlaut. I don't know which one it is. Which O has the umlaut? Always forget about the umlaut. Bootes. The second one. Okay, cool. Let's put in the umlaut because it's not every day you get to make an umlaut, you know, unless you're Swedish or something. Okay, so 1627 -26. (16, 24, 28, and then 1627 -26. So we want to go down 10, -20, -26. You guys see that?
Antares.
Antares. And Antares means anti-Mars. It's a very red giant star that people confuse for Mars. Let's see what constellation Antares is in. There's boundaries here. We have to not cross the boundary. Antares is connected down here to Scorpius.
That's me.
One last one to go. 1836, +39. So 18, 20, 24, 28, 32, 36. So that's 1836. Positive 39 is almost 40. So 10, 20, 30, 40.
Vega.
The star
Ego.
and the
Vega.
constellation is Lyra. Lyra is a harp. So Vega
Oh.
and Lyra. And those are the 10 brightest and most famous stars in the sky with their constellations. Notice each one has a unique right ascension and declination, and therefore can be properly found on a celestial globe. Okay, we're going to do two more little parts. We're going to do table 2, and we're going to do table 3. They don't take too long. For table 2, they want us to find the positions of the planets tonight. There are 5 classical planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. And we're going to try to identify what constellation they're found in tonight. To do this, I'm going to use a something called an ephemeris table. Astronomers record the positions and the forecasts of planets and stars in an ephemeris. There's kind of a cool one, ephemeris.com, okay. And it's got the right ascension and declinations of the 5 naked eye planets tonight. So let's write them down here. I'm going to put this in the tape, okay? And I want you guys to kind of work with me and kind of do what I'm about to do. Let's make a little chart here. So this is going to be our right ascension, and this is going to be our declination. And then we'll have the constellation kind of over here, all right? Mercury is currently at a right ascension of 5 hours and 35 minutes. Notice how I wrote that, okay? And the declination is 0 degrees 56 arc minutes. The arc minutes don't matter so much. Venus is at 524, it's pretty close in right ascension. And it's pretty close in declination too, 0 degrees 41 arc minutes. Wow, it looks to me like Mercury and Venus are in what we call conjunction. They're found in roughly the same position on the celestial sphere. That'll be interesting. Mars is located at 7 hours and 29 minutes. Declination positive 1 degree, 22 arc minutes. Jupiter is 22 hours and 14 minutes. Negative 0 degrees 51 arc minutes. Wow, everyone's really close to the celestial equator today. And Saturn is 2104. Wow, all these planets are like bunched up. I think that must mean something. It must mean that I'm having Indian food for dinner. I don't know. Consult your zodiac charts. Okay, the declination is negative 0 degrees 38 arc minutes.
Can I ask a possibly stupid question?
Sure enough.
For the 0 degrees, if 0, I don't know, because how can 0 be positive or negative?
Because it's not exactly 0. It has some increment in arc minutes or arc seconds. For instance, if this is 0 degrees, it's neither positive or negative. but let's
Yeah.
say that's +1 degree, and let's say that's -1 degree. Remember, we can break them up into arc minutes, right? Into 60 little wedges and 60 little wedges.
Oh,
This,
yeah.
right? So that tells me that Jupiter is 0 degrees and down 51. So Jupiter's like over here, right?
Yeah.
And Saturn is -0 degrees and 38. See what I'm saying?
Yeah.
And these are 41 and 56. So Venus is like, you see what I mean?
Yeah.
It's splitting fractions of a degree.
Okay. That makes
Right?
sense.
Okay.
Thanks.
All right, let's go ahead and find the constellations. By the way, they don't actually print the planets on this globe. Why not? Why aren't the planets printed on the globe?
They're never in the same spot.
Yeah, the
Constellation.
planets move. That'll be a big part of next class's lecture. Planets wander and drift along the globe. Very good. In fact, the Greek word for planet, planetos, it means wanderer. Okay, so let's go to 5 hours here. Hold on a sec. Oh. 5 hours and 35 minutes. And then, I don't like this. I don't like this at all. Something is really wrong. That is not possible. 5:35, 0 degrees. I screwed up somewhere. Do you guys understand why that's not possible? How do I know that's wrong? 5 hours and 35 minutes and barely even 1 degree. Can a planet appear in the constellation Orion?
No.
No. So I screwed up. Orion is not a zodiac constellation. What the hell did I do? Oh, wow. I took the column latitude. I should have, oh God, what a moron I am. Okay. It's, okay, my declinations are all wrong. I'm sorry, guys. Wow, I'm dummy. Okay, here's what we're gonna do. We're not even gonna mess around with arc minutes anymore. I just read from the wrong column. I don't know what the heck is wrong with me. Wow. Major dumb. Major dumb. Okay. The declination, positive 24 degrees. Forget about the arc minutes. They don't matter. Positive 24 degrees. Positive 23 degrees. Negative 12 degrees. Negative 17 degrees. Okay, you guys got that? So, oh, sorry, my phone went dead here. Positive 24, positive 24, positive 23, negative 12, negative 17. The right ascensions were correct. Sorry about that, everyone. Nicole, let me know when you're ready to go on. How about Nina? You good? Okay. I just don't want to go too quickly for you guys. Let's just check in on that, okay? All right. In fact, all right, this is cool. I can kind of see everyone right now. All right, let's try that again. 5 hours and see how I used my astronomy knowledge to figure out that I screwed up? That's a good thing, okay? So 5 hours and 35 minutes. And now we're gonna go positive 24 degrees, positive 10, positive 20, positive 24. What constellation am I in?
Is that Taurus?
Yeah,
Taurus.
very good. Wow. Yeah. Get out of here. Okay. Taurus. Okay, I suspect that Venus is also going to be in Taurus, but let's just check. 524 is like here, and then positive 24 is also in Taurus. Okay, they're so close to each other that they're. Now that means Mercury and Venus are kind of in the same constellation tonight. Okay, Mars is 7 hours and 30 minutes. So we'll go over here to 7 hours and 30 minutes. It's right in the middle. And it's positive 23, positive 10, positive 23. This is definitely not Taurus. I can tell by these two stars and these stick figures that we're actually in the constellation of Gemini. That's Castor and Pollux there, the two heads of Gemini.
Oh, it's Gemini.
That might have been a little tough for you guys to see. Sorry about that. 2214 and negative 12 degrees. So let's go around here. Okay, sorry. Okay, 2214, maybe about there. A quarter turn, negative 10, negative 12. Can you guys see our constellation?
Aquarius.
Aquarius. And I suspect the next one's going to be close. (2105) negative 17. 2105 is just after 21 hours. And negative 17 is down 10, down 20, back of it. We're actually in a different constellation. Can you guys see that?
Capricorn.
Yeah, Capricornus.
Capricornus.
Now, these are the constellations that the stars are, the planets are in tonight, according to this globe. But I'd like you guys to pay attention to something. Do you see this here? This globe was printed by the Triponese Planetarium Corporation in Saginaw, Michigan in 1967. Let's think about how many years old this globe is. 21 minus 1967. 54, Jordan, 50 comments from the peanut gallery here. 54 years old. Now, you guys might remember that Earth undergoes something called a 26,000 year precession. Let's see if I can find a picture of that somewhere. The moon exerts these kind of gravitational warbles on Earth that over long periods of time cause it to change the orientation of its axis. And the motion is known as precession. I just have a little crummy picture from the book here. Yeah, 27, slide 27. I'll get out of here. Function F5, 27. Okay. So let me push you guys off to the side for a second. Okay. Notice, if you will, that today Earth's axis points towards the North Star Polaris. But if we were to wait 15,000 years from today, Earth's North Pole is going to precess and point towards the star Vega. And what this means is that every 50 years or so, astronomers need to update their coordinates for something called precession. Now, we're not using epoch 1950s coordinates anymore. We're now using probably epoch 2050 coordinates. So when I actually look at the website for Sun to Sedna, you'll notice the constellations have drifted a little bit over the course of 50 years. In fact, tonight, Mercury and Venus are in Gemini, Jupiter is in Cancer. Sorry, Jupiter is in Pisces. Mars is in Cancer. Saturn is in Aquarius. They've all shifted by roughly one constellation. It's okay that we're keeping those because we used an old-fashioned globe to get these answers. Obviously, you'd want to use a more modern one to do it proper. It is also for this reason that whatever you think your astrological sign is the sun was no longer there on your birthday, because most people are using out-of-date coordinates for your co-star and your astrology columns because they don't know what the fuck they're doing and they're making it up, okay? We'll demonstrate that in a moment. For now, we've got one more mini task to do and then we can call it quits, okay? This should look familiar to you based on what we did a few moments ago in our homework. In table 3, we're supposed to move the sun to these random dates, and we're supposed to get the right ascension and declination. And notice here that you can see on this globe, there are dates for the sun that move along the ecliptic. The first one that we're supposed to move to is over here, March 1, 5, 10, 15, 20, and boom. If I move the sun to this position, that's March 21st. So I'll try to move the angle correctly. What would you guys say is the right ascension and declination of the sun on March 21st?
Positive 20.
What are you giving me there? Declination or right ascension?
Right ascension?
There is no.
Oh, no, I'm sorry, the declination.
But declination is measured north or south of, or positive or negative from the celestial equator. And this seam is the celestial equator, right?
Oh, I got you. Okay.
So try again.
That's a 0 almost.
That's right. It's on the celestial equator. So its declination is 0 degrees. What about its right ascension? What would you guys say?
25?
Huh?
20.
Oh, I looked at it wrong. It'd be 20.
No,
I looked at-
a right ascension of 20 is over here. That's 20 hours.
Oh.
We're over here.
Is it
Right
0?
ascension is measured in hours.
Is 0 hours?
Yeah, you can see right there, the 0 hour goes right to the sun. And the way we write that is, 0, 0, colon 0, 0, okay? Let's try June 21st. Are you guys understanding what's going on here?
Yes.
What's going on? Someone explain it to me. There's June 21st. Okay, let's try to orient our globe sort of like so. What is the, what's the declination? Okay, well, this doesn't perfectly line up because, you know, they probably, some little kid in Bangladesh probably made this thing and they didn't beat him hard enough or something. It's a little wiggly and out of whack. Okay, so what are we supposed to get? Someone who understands? Positive 10.
Should be a positive, yeah.
Huh? Positive what?
Positive 20 something. Can't see.
Yeah, 20. I wonder what positive 20 what?
23.
In fact, I'm willing to bet it's even a declination of positive 23.5 degrees, right? What's the right ascension?
Six.
6 hours. Do you guys know what any of the other answers are here?
It's all
God.
of the solstices and the equinox.
These are the equinoxes and the solstices, aren't they, Nicole? So what's September 21st going to be?
Right ascension is going to be 18 hours, and the deck.
No, this is the fall. Sorry, this is the fall equinox. The fall equinox is September 21st.
oh, sorry. The fall is gonna be
Oh,
12 hours for the right ascension and then 0 degrees.
Yep, so there's our 12 hours. And it's still on the celestial equator, so 0 degrees. Okay. Okay, how about the December 21st?
18 hours
Yep, 18 hours.
and negative 23.5.
Yep, you can see it's below negative. All right, cool. Every day the sun has a new right ascension and declination. Why don't we estimate it off our globe? Today is 5/26. Okay. Let's move it to May 26th and see what happens.
April, May, about
Well-
5 hours.
Huh?
Somewhere around 5 hours, right ascension with,
Yeah, you might even be able to guess it, right?
yeah, going by, the June is 6 hours right ascension. We're in May, so
May 26th.
26.
So you're not too far off.
4
So
point something.
it looks like this is June. So here's May. May 26th. 4 hours, 5 hours, 4 hours and 4 minutes, 8 minutes, 12, 4 hours and 12 minutes, maybe. That's my guess. And what would you say the declination is here?
Positive 19, somewhere around there, positive 20.
Pardon? Positive what? It's between 10 and 20, so.
18 maybe?
Yeah, all right, fine. Let's compare it to the true value that the ephemeris.com gives us and see how well we hit it. I'm kind of curious to see how well our globe compares. According to this, oh, wow. 415
Wow.
and positive 21. We weren't too bad, were we? Our right ascension was only off by 3 minutes. Our declination was a little sloppy, but that's okay. I'd say that's a pretty fine damn job. Okay, one more thing. I'd like to show us for our last work of art that your birthday most likely no longer corresponds to your zodiac sign. Nina, here's what I want you to do for me, Nina.
Yes. I'm here.
So for Nina, you guys can write, each one of you can write this down here. So what is your birthday? Just give it to me as a month/day, just like I have here.
It's October 9th.
So 10/09, right? Okay, and what is your sign supposed to be according to like the fortune cookies and stuff?
Libra.
Okay. And now let's make a column for her real sign, okay? So let's go to October 9th and see where the sun was at on Nina's birthday. September, October 9th. In what constellation was the sun on your birthday, Nina?
Virgo.
Wow. So you used to be a Libra, but the sun was actually in Virgo on your birthday. So what does that mean, Nina? Are you actually a Libra or are you a Virgo?
What?
Oh,
You can't be both. Obviously, Libras, they like taking roller coaster rides, and Virgos like baking brownies. That's not possible. You can't be both. No one could possibly do both of those things. Okay. How about Kyle? Kyle, what's your B-day?
August 16, Leo.
And you're supposed to be a Leo. Let's head on over here to August 16. Actually, you're one of the strange ones. August 16th is still in the constellation Leo, probably because Leo is a really long constellation. You get to still be a Leo, okay? How about Nicole? Nicole, what's your birthday?
July 11th.
July 11th. And what are you supposed to be?
A Cancer.
Where the sun was here, July 11th on your birthday. What constellation was the sun in on your birthday?
Gemini.
Sorry, you're a Gemini now. Okay. Jeff, what's your birthday?
Mine's November 2nd.
November 2nd. All right. You're all over here on the same side of the globe. So that's cool. And what are you supposed to be?
Scorpio.
Well, according to this, November 2nd is about here. You can see there's boundaries to that constellation. And sorry, bro, you're a Libra now.
Means I got a big brownies.
Just don't put too much you know what in there, or you might start believing this stuff. You know what I'm saying? Okay, so well, you've done it, guys. You've wasted another day with me here learning about astronomy. And you know, those 2 pages, turn them in. That's lab 2. Before I break with you for the week, I want to just one more time review with you guys what I need from you this week. We all just did lab 2 together. So boom, that's done. Take a picture of both of these pages and submit it. If you were Nina, or I guess we lost, what's her face?
Whitney.
Whitney, thank you. We lost Whitney, but she was here earlier. So Whitney and Nina have definitely done their homeworks. The rest of you guys are going to have to go back and watch the homework video, okay? Luckily for you, I chopped off one of the problems, and there's only 4 problems. It will take a couple hours to watch it, maybe an hour and a half or so. Unfortunately, when I stop this video, it's going to begin to render, and then I'm going to upload it to YouTube. So I'm anticipating at least 2 hours or so before I can have that posted. Sorry. There are versions of this homework from previous semesters if you want to scroll down. But I say give yourself a break and do it later tonight or tomorrow. I need those 3 assignments, Lab 1, Homework 1, and Lab 2, submitted to me by Sunday at 11 p.m. Is that something that is reasonable? Can you do that? All right,
Yes.
That's not too bad. You just have to sit there and copy. Now, one last thing before I go. Since I've got a few more victims here today, let's just talk a little bit about submissions here. We'll probably see that. Let's see what people have been submitting to me. And I want you guys to see what it looks like on my end so you know what is okay and what is not okay. If I go over here to my grade center to needs grading, I can see that a few people, oh wow, have already submitted their stuff. Let's take a look at our submissions for Lab 1, and let's see who's been naughty and who's been nice to me. I want to show you the kind of things that I can deal with and sort of things I can't deal with. So this person submitted a JPEG and I can read it. Fine, that's good. They're going to get 10 out of 10 points. They did everything I wanted. Here's Whitney. Whitney, that's good. Everything wow, okay. All right, well, yeah, that's good. Emmanuel, you were here a few moments ago. Emmanuel, that looks great. So far, you guys are doing everything right. It's only a matter of time before I see something that pisses me off. This is good. This is what I want to see. Make sure you can see things in the preview box. Try not to.
Sorry, I didn't mean to interrupt you. I was just going to ask for Lab 1. Are we only submitting the first page?
Yeah, just that first page, because that's all we had time to work on, I believe.
For Lab 1, right?
Yeah.
Okay.
That's how I remember it anyways. Okay. Let's see. Okay, this person didn't have a printer, so they had to write it out. But this is acceptable. It's going to get tricky as things go. This is okay, okay? They wrote out all the questions, and I can see that. Obviously, it's cooler if you can see the sheet, but this works if you're in a pinch. He's apologizing, but Joseph, if you watch this later, I accept this, okay? That's fine.
Oh, I'm right here.
Oh, you are here. Okay. Hey, what's up, buddy? Oh, where are you?
Oh, yeah. On Joey, yeah.
Well, that's Joey. Sorry. I thought that was Joseph. I apologize. So far, everyone's doing stuff I like. Geraldine, I would have liked it if you put your section in lab number 1. That's going to help you keep shit straight later on. Notice that all the other students had that info. That's what I want, right? I want here AS1010. Well, this person, Joe, I wanted to see lab number 1 at the top. Let's see somebody else who did it better. Yeah. No, she didn't do it right either. God damn it. Guys, no one can follow the fucking instructions. Nope. I just want to see lab number 1 so that when I tell you later on, hey, you screwed up, okay? You screwed up. Where's your lab 1? I know what you're going to say to me. You're going to be like, I don't know. I don't know what I did. But look, if you did what I told you to, you'd see your name and you'd see lab number 2 and 10. See what I mean? That turns out to be smart stuff to do. If you and I have a disagreement about what you turned in later, you can say, look, I got lab number 2 right here. That's lab number 2, okay? So please get in the habit of doing that stuff. It's smart.
In the video for the lab, you didn't tell us to do that, so that's why.
That's right. I forget. Sorry, I did this with astronomy 1020 yesterday. Okay, so then that's my bad. Right. I forget. See, because I do this every day and I do it with different groups, I kind of forget who I said to what. I apologize. So that's my bad. You got me, Nicole. Okay. But from now on, can we do that just the way we did it here today? That's good. Things are a little different during the spring semester because then I have like hundreds of students and then it gets really, really messy. This isn't quite as bad. Okay. I don't want to take any more of your time. I really appreciate it was fun hanging out with you guys. Let's talk about what happens next week. Next week, we're going to start homework 2. We're going to do a lecture 3, and then we're going to do lab 3, correct? Things are going to move quite quickly here. So I'm going to do just like I did today. If you can join us, I'm going to do an office hours session at 10 a.m. on Monday. Okay? Oh, shit. Thank you, Jordan. Hey, Monday we don't have class, right? Monday is Memorial Day. So I want to point something out to you guys that I meant to go over on the first day. If you look at our syllabus here, sorry, the schedule is what I want. Because Monday is Memorial Day, CCRI has an official makeup day on Friday. I hate this. I hate it more than anything. But I feel duty bound to follow the CCRI schedule because they cut my paycheck. You know what I'm saying? Okay, so I'm going to do my job so that I get paid. We will not have class on Monday. We will have class on Wednesday, a week from today. And then the makeup day is Friday, June 4th. Okay? So it's like
Is
you
the
didn't even...
time-
Huh?
The timing is the same, like 10 to 4.
Same exact thing, yeah.
Okay.
I know some people have work schedules and stuff. I don't know. This is my work. So I'm going to do what I'm supposed to do. I'll hold class on Friday. Okay. We could all do a pre-recorded one, but I think some of you like that live experience. I'll provide it for you on Friday if you want it. So I will see you guys not Monday. Thank you, Jordan. I will see you on Wednesday, a week from today at 10 a.m. And then I will see you again on Friday. Make sense?
Hey, quick
You
question,
guys-
Professor.
Yeah.
Is the observatory open up at the campus yet?
So that's a great question. They told me I can start opening it in the fall. And that's kind of works for me because I'm doing a research project with one of my students from last semester. So I've got a big piece of equipment attached to the telescope right now. But the weather's nice and people want to come out and look at stuff. And I'd like to show that to you. So the answer is no, not for now, Jeff. It will be open soon. But you know what I was thinking, Jeff, is maybe sometime towards the end of the semester and at the beginning of the next one, maybe I can take the spectrograph off and have a night when I go there and invite you guys to come out and look at stuff, you know?
That'd be awesome.
Yeah, it won't have to be like required because I know people have stuff going on in their lives. But if enough of you would like to come out and take a peek at some stuff, it's pretty cool to see the moon through the telescope. It's really wild. And so we could do a viewing at the Peerless Roof downtown or something like that. So I'll try to concoct something so that you guys get to look through a telescope. I think that's something that you deserve to experience if you're taking this class. That keeps it real.
Awesome.
So keep me on tack on that, Jeff. We'll figure that out towards the end of the semester, okay?
Yeah, thank you.
All right. All right, guys, I will see you a week from today then, correct?
Yeah.
right.
And then Friday's the makeup day that week.
Yeah, not this Friday, but the Friday after next, right? So That's Friday, the 4th of June. Okay?
Yep.
All right. See you next week. Bye.
Thank you.